Welcome back. Let's review for your financial mathematics final exam. Okay, so in this video, we are going to be working through some review problems to help you prepare for a final exam in financial mathematics or help you prepare to take the Actuarial Exam FM. Specifically in this video, I have 15 review problems that we're going to work through, and there are an additional 15 available exclusively on my membership site. I'll talk more about that at the end of this video, but in total between this video and the extra examples there, that would be 30 review problems, which is actually the same number of problems as you would see on the Exam FM if you are preparing to take that exam. Okay, and before we get started and begin working through the different review problems, there's a couple of things I want to make sure to mention. The first thing is that if you want to get the most out of this video, I highly recommend that you try each and every one of these problems for yourself first before you watch me work through them. Really try to challenge yourself. Treat this as if it were an exam that you were going to be graded on, and try to solve these problems and pick the correct solution. Unlike my example problems in my other financial mathematics videos, all of these problems will have multiple choice answers for you to pick from, so you really could treat this as an exam if you wanted to. In fact, I have a free worksheet set that you can download that goes along with this video. It has all of the review problems that we are going to take a look at, so you could download the PDF and print it out and use it as a practice exam. And so if that's something that you would like to have or use as you watch this video, feel free to do that. Feel free to download that free PDF. The link for it will be in the description of this video. Okay, so that's the first thing I wanted to mention. And the second thing is that for these example problems in my solutions, I'm going to be exclusively using the BA2 Plus financial calculator. If you don't have one of those calculators, you probably should get one. They are extremely helpful for solving a lot of these FM problems. If you don't have a financial calculator, there are certain scenarios or certain problems that are pretty difficult and possibly even impossible to do otherwise. So you want to have that calculator available. Okay, and that is going to be a little bit different. If you've watched the majority of my financial mathematics videos, I don't really pull out a calculator too often. I usually just say, if you put this into a calculator, here's the answer you will get. But in this video, I'm not going to do that. I am actually going to show you the work that you need to do in the calculator to get to the final answer so that hopefully every question you may have is answered. I want these solutions to be as clear as possible and to be as helpful as possible for you as you review for your exam. Okay, so that was the second thing I wanted to mention. Make sure you get a BA2 Plus calculator. And then finally, the third thing that I wanted to mention is that this is a review focused on the concepts that are tested on the Actuarial Exam FM, and that's it. So that means I'm going to cover interest rate measurement, the valuation of annuities, bond valuation, amortization, a little bit of cash flow analysis, cash flow duration, and cash flow immunization. Okay, so basically everything I covered in my financial mathematics series, minus a few of the concepts that are no longer tested on the Exam FM. Okay, so if you have not watched the majority of those videos, or if you're not familiar with the concepts that are tested on the Exam FM, be sure to do that first. Be sure to get familiar with those concepts and know what you're going to be tested on. Otherwise, these problems are going to be very difficult and you're not going to know what you're doing. In this video, I'm going to assume that you know the concepts that we are working with. I'm not going to explain everything from scratch, but obviously I will give you some reminders here and there about different formulas and the way different things work. But ultimately, I am going to assume you know what we're talking about. And with that being said, I think that's everything I wanted to cover before we get started here. If you're going to take my advice and try these problems out for yourself, then get ready to pause the video because I'm going to get started now. Let's move into our first final exam review problem. All right, so here's our first review problem. We have Keaton purchases a perpetuity immediate for $12,000 that has a constant force of interest of 0.08. The annual payments of the perpetuity decrease by 0.5% each year. Determine the amount of the perpetuity's first payment. Okay, so the first thing that stands out to me in this problem is that we are working with a perpetuity. So that means that there are payments being received or payments being made forever. So we're not going to be working with our typical annuity formulas, most likely. We're going to be working with some special formulas related to perpetuities. In this case, the annual payments of the perpetuity are decreasing by 0.5% each year. So that means that we are working with a geometric perpetuity. Remember that an annuity, or in this case a perpetuity, is geometric when the payments increase or decrease by a percentage, like they are right here. This is not an arithmetic perpetuity. An arithmetic perpetuity would be if the payments are increasing or decreasing by a set amount, something like $5 or $10 or $15 every period. Okay, that's not what we have here. We have a geometric perpetuity because the payments are decreasing by 0.5% each year. That's a percentage. All right, now to get a better idea of what we're really working with here, I am going to draw out a timeline. This might not be necessary if you are pressed for time. You could probably get away without this, but I am going to draw one here just to help you understand the solution to this problem. All right, so right here will be time equals 0. And then this would go on forever, so I'm just going to include about 4 or 5 payments here. So we'll do time 1, time 2, time 3, time 4, and time 5. So let me write those dates in here. I believe these are annual payments, right? It does say the annual payments of the perpetuity decrease by 0.5% each year. So each of these times on the timeline represents a year. Now, we're told that he purchases the perpetuity immediate for $12,000, so that would be its present value. When you're told that something is bought or it's priced at a certain value, that is the present value of that investment or that set of cash flows. So in this case, the present value is $12,000. Okay? Now, for the actual payments of this perpetuity, we don't know what they are. We know they decrease by 0.5% each year, but we don't know the actual amount of the initial payment and then what all the other payments would be after that, even though we know they decrease. So I'm just going to represent that with X. All right, we're going to say that this perpetuity would have a payment of X at time 1. Then at time 2, it's going to decrease by 0.5%. Now, what does that actually mean for our inflation rate here? Well, we know that R is equal to negative 0.5%. That's our inflation rate. Because the payments are decreasing, the inflation rate is negative. But as an actual decimal, R would be equal to negative 0.005. So the amount of our next payment, our first payment is X, but then if that payment is going to decrease by 0.5%, what we would do is take that payment and multiply it by 1 plus the inflation rate. So you'd have 1 plus negative 0.005. So if you did that, you would get 0.995. Okay, so that would be the second payment. It would be the amount X of each annual payment, but now decreased by 0.5%. We just want 0.995 of that original payment. And then every payment after that will also decrease by another 0.5%, so we need to multiply by another factor of 0.995. So at time 3, we would have X times 0.995 squared. At time 4, you would have X times 0.995 cubed. And at time 5, you would have X times 0.995 to the power of 4, and so on. This would obviously go on forever because this is a perpetuity. All right, now our final goal here in this problem is to determine the amount of the perpetuity's first payment. So that would be X, that's what we let X be equal to. And in order to do that, we will need to set up some type of an equation that involves the values that we do know and this payment amount that we don't know. And the easiest way to do that, in this case, would be to set up the equation for how we would calculate the present value of this perpetuity, right? We were given the present value right here. We know it's 12,000. And in order to find that present value, you would calculate the present value of all of the payments. Okay, now if you learned how to calculate geometric annuities and perpetuities from my videos, then you'll know that I recommend a 2-step strategy for calculating the present value of a geometric perpetuity. The first step is to simply just value a couple of the payments at time 0, set them equal to the present value, and then after that use a formula. And I'll show you that formula in a second, but let's just start with the first step and value all of these payments at time 0. All right, now obviously we can't value all of them. This is a perpetuity. We would be here forever if we tried to value every single payment at time 0. In fact, we'd never finish. We'd be doing it forever. But I'm just going to write a couple terms. Really, you only need to write one term and I'll tell you why in just a second. But the present value of this perpetuity is 12,000, so that would be equal to all of these payments of the perpetuity valued at time 0. For the first payment, we just have x, but that would need to be brought back one period. So we have x times a present value factor to the first power. Then we'll add that to the next payment, which is x times 0.995. That needs to be brought back two periods. So we'd have x times 0.995, and then that will be multiplied by v squared. And you could continue on from there. You could add the next payment brought back 3 periods, the next payment brought back 4 periods, but we don't really need to do that. That would be a waste of our time. Let's just stop there, because here's the formula. This is what I recommend that you use for calculating the present value of a geometric perpetuity. The formula is that the present value is equal to the first term of that equation we just set up, divided by 1 minus 1 plus the inflation rate, which we represent with r, divided by 1 plus the interest rate. Okay, this is the formula we are going to use. In this case, the first term of our equation is x times v. All right, so that is what is going to go in the numerator of our calculation here. So if we set this up, we know that 12,000 will be equal to that first term of x times v divided by 1 minus 1 plus the inflation rate, which would be 1 minus 0.005. So that'll just get us 0.995. And then we're dividing by 1 plus the interest rate. And now things get a little bit tricky, because what is our interest rate? Well, we have to go back to our problem here. We're told that this perpetuity immediate has a constant force of interest of 0.08. Okay, so we've been given delta is equal to 0.08. That is not I. All right, that's not the interest rate that we need for this calculation. That interest rate I needs to be the interest rate that matches the payment cycle for this perpetuity, which in this case, it has annual payments, so we need an annual effective interest rate. So we will need to convert this force of interest that we've been given to an annual effective interest rate. So let's do that real quick. I'm going to do that over here. Remember that a constant force of interest is equal to the natural log of 1 plus the annual effective interest rate. So if we know that the force of interest is 0.08, we can set that equal to the natural log of 1 plus I and work on solving for I to get rid of the natural log function. We want to make both sides of the equation the power of e. The exponential function e and the natural log function are inverse functions, so they cancel each other out. So we'll have e to the power of 0.08 is equal to e to the power of the natural log of 1 plus I, but e and the natural log, as I just said, will cancel each other out, leaving us with what is inside the natural log function, which will just be 1 plus I. So we have 1 plus I, which means that I, our annual effective interest rate, will be equal to e to the power of 0.08 minus 1. You would just subtract 1 from both sides to solve for the annual effective interest rate. All right, now this is where you're going to need your calculator. So let me just write I equals, and now pull out your BA2 plus. We need to take e to the power of 0.08 and subtract 1. So I'm going to put in 0.08, and then we need to hit e to the power of x, which we get to by first hitting the second button and then the natural log button. And that takes e to the power of whatever was on our screen. So we get 1.08328 and some more decimals. So I'll write that down here. I is equal to 0.083287 and some more decimals. Now, that is what we need to use in this denominator here. In this formula, we need 1 plus r divided by 1 plus I. And 1 plus I will be 1.083287 and some more decimals. I'll just round it off like this. We'll have 1.0832 and more decimals. All right, and that is the interest rate that will also be used in this present value factor, okay? Remember that a present value factor is equal to 1 divided by 1 plus the interest rate, so this would be 1 divided by 1.0832, okay? So now everything is set up. All we have to do now is solve for x in this equation. So here's what I'm going to do. If I rewrite this equation, we're going to have 12,000 equal to x, and then I'm going to multiply it by the present value factor, which would be 1 divided by 1.0832, and that would be multiplied by the rest of this fraction, which would be 1 divided by 1 minus 0.995, divided by 1.0832. Okay, and remember that there are more decimals for both of those values there. But now let's do this calculation. We're going to multiply these two fractions and then divide both sides of the equation by those fractions and then divide 12,000 by whatever that is, and that will solve for x. Okay, so in our calculator, we currently have 1.0832 and some more decimals. So I'm going to store that in the 1 button just in case I lose it. We might need that later. So store it in the calculator like I did. And now we first want to calculate 1 divided by that. So an easy way to calculate that is to just press the reciprocal button on the calculator. There's that. Then we want to divide it by 1 minus 0.995 divided by 1.0832. All right, so we're going to come back to the value that's currently on my calculator screen. I'm going to store that in the 2 button. And then what I'm going to do is take 0.995, divide it by 1.0832, which I stored in the 1 button. So I'll hit recall 1, hit equals, and then I'm going to subtract that from 1. And the easiest way to do that in the BA2 Plus calculator, just because the way things are, I'm going to subtract 1 and then make it positive. Okay, that's the same thing as subtracting it from 1. You just subtract 1 from it and then change the sign to positive. Okay, so that's what's in the denominator. We have 1 divided by that value that we just calculated in the calculator. So really, if we hit the reciprocal button, that would be 1 divided by that value. And now we want to multiply that by that other value we calculated, which I stored in the 2 button. So I'm going to multiply by recall 2 and then hit equals. And there's the value of those 2 fractions multiplied together. So that's what's being multiplied by x. I'll write that down real quick. We have 12,000 equal to x multiplied by 11.3267 and some more decimals. And now if you divide 12,000 by that value, you'll have solved for x. So a quick way to do that is to hit divide by 12,000, which yes, is the opposite of what we wanted to do, but then we can just hit the reciprocal button and that reverses what we just did. Remember that the reciprocal of a fraction is just the same fraction, but you reverse the numerator and denominator. So if you divide by something and then hit the reciprocal button, it's essentially the same as dividing the other way, if that makes sense. Okay, if you want to get fast at solving these problems in the calculator, you have to learn little tricks like that along the way. That's just something that I like to do. All right, but there it is. That's the final answer. X is equal to $1,059 and about 44 cents. That's the value we get in our calculator. And comparing that to our answer choices here, it looks like answer choice B is the correct answer, right? B is 1,059, which is basically what we got. Okay, so I will box that in. That is the final answer to this problem. Let's move on to the next one. Okay, for problem 2, we have a 20-year $1,000 bond with 4% coupons payable semi-annually, matures at par value. The bond is purchased to yield 6% convertible semi-annually for the first 10 years and 5% thereafter. Find the accumulation of discount for the 5th coupon. Okay, so in this problem, we are working with a bond, but we're also working with bond amortization. The way I know that is because we are asked to find the accumulation of discount for the 5th coupon, which essentially just means find the amount of principal in the 5th coupon payment. Okay, so that's our final goal here. That's what we want to find. But before we can do that, we will probably need to work with the other values that we've been given. And something that's interesting to note about the bond in this problem is that it doesn't have the same yield rate for the entire problem or for its entire maturity, right? It's purchased to yield 6% convertible semi-annually for the first 10 years, but then it has 5% thereafter, which would be the last 10 years, because this bond is a 20-year bond, and that's kind of weird. We don't typically see bonds that have different yield rates. Usually they have the same yield rate for their entire term length. So that's probably going to come into play at some point in this problem. All right, but the first thing I want to do here is just write down all the information we know about this bond. That way it's easy for us to reference those values as we go about solving the problem. First of all, we know that this bond pays semi-annual coupons, right? It has coupons payable semi-annually. So if there are 20 years for the bond, then that means that there will be 40 semi-annual periods and 40 coupons. So N is equal to 20 times 2, which is equal to 40. There are 40 periods for this bond. The par value is 1,000, and we're not told anything about the redemption value, so we can just assume that the redemption value is the same as the face value or par value. So F equals C, which is equal to 1,000. And then we have 4% coupons payable semi-annually. Remember that those rates are given as nominal rates convertible semi-annually, unless you're told otherwise. So for the coupon rate, we will have 0.04 divided by 2, which is equal to 0.02. We have a 2% coupon rate. And then we have two different yield rates. So the first one is a 6% yield rate convertible semi-annually. We can assume that that is also a nominal rate. So to get the actual semi-annual effective yield rate, we need to take 0.06 and divide it by 2. That gives us 0.03. That is for the first 10 years. And then the second yield rate is 5%, or that's what it is as a nominal rate. So we would take 0.05 divided by 2 and get 0.025. That's for the last 10 years. Okay, so those are the two different yield rates that we are working with. And then finally, the thing we want to find in this problem is the principal at time 5, or the amount of principal in the fifth coupon. That is what we don't know. That's what we want to find. And if you know your shortcut formulas, you might be tempted to pull out this formula that I've shown before in my other financial mathematics videos, that to calculate the principal at any time t for a bond, what you can do is take the face value, multiply it by the coupon rate minus the yield rate, and then multiply that by a present value factor to the power of n minus t plus 1. And of course, that present value factor would use that yield rate j. However, we can't use this formula in this problem because this formula assumes that that yield rate doesn't change for the entire time to maturity for the bond. And that's not true in this problem. We have two different yield rates for different sets of years, so this formula is not going to be helpful. Don't use this. It's not going to work. So we have to find another way to calculate the principal at time 5. The easiest way is going to be to use the BA2 plus calculator, but in order to actually calculate the principal using the amortization feature of the calculator, we do need to know the price of this bond. Okay, and we would also need to know the price if we were going to do this by hand, because what you could do is go through the cycle of calculating the interest at time 1, then the principal at time 1, then the book value at time 1, then doing the interest at time 2, the principal at time 2, and the book value at time 2, and so on until you get to the principal at time 5. You could do that as well. That would take a ton of time. You probably don't want to do that. But if you were going to do that, you would need to know the original amount of the loan per se, but we are working with a bond, so the loan amount would be the price of the bond. You would still need to know that, okay? So somehow we need to calculate the price of this bond. We currently don't know what it is, so let's work on that. In order to get an idea of how you would go about calculating the price of this bond with two different yield rates, I am going to draw a timeline. Typically, I don't draw timelines for bond problems because they're not really necessary. They can be helpful visuals, but ultimately will slow you down. In this case, I do want to draw one to help you visualize the calculation here. Right here, I'm going to have time equals 0, and then at the end, we will have time equals 40, and in the middle would be time equals 20. Now, our first yield rate of 3% is active in those first 20 semi-annual periods, or the first 10 years, and then this yield rate of 2.5%, that is active for the last 10 years, or the last 20 periods. So keep that in mind, and don't forget that at every moment in time, starting with time 1, you're going to get a payment of a coupon, which would be F times R. Okay, now I'm not going to bother to write all of those coupons into this timeline, but we would want to calculate F times R, which in this case would be 1,000 times 0.02, which would be 20. So our coupon amounts are of $20. So you would have 20 at time 1, at time 2, time 3, time 4, and so on, all the way up to time 40. So I'm just going to do this. We would have $20 payments or $20 coupons at every time up to time 40, where we'd have another coupon payment as well as the return of the redemption value, which is $1,000. Okay, so we'd also have 1,000 at time 40. So what we would have to do here to calculate the price of this bond is value the first 20 coupons at time 0 using this yield rate, and then value the last 20 coupons as well as the redemption value using this yield rate. And if you were going to do that with your traditional bond formula, here's what that would look like. We would be calculating the book value at time 0, which is the same as the price of the bond. So the price is equal to the present value of the first 20 coupons of $20. So we'd have 20A 20 bracket the yield rate for those first 20 periods, which is 0.03. And then you would add that to the last 20 coupons of $20. So you'd have 20 times A 20 bracket, and then the interest rate or the yield rate for those 10 years, which would be 0.025. But now this is calculating the present value of all of these payments that would start at time 21. And so this present value would be valued at time 20. So we would need to bring it back another 20 periods to actually value it at time 0, where the price is valued. So we would need to multiply by a present value factor to the power of 20 that uses the yield rate for those first 10 years or first 20 periods, right? This notation currently values all of these coupons at time 20, so we need to bring it back to time 0, and for that period of time, the 3% yield rate is active. So we would need to use 0.03 as the yield rate for that present value factor. So that takes care of the coupon payments, but then we would need to add the redemption value of 1,000 valued at time 0. So we would need to bring it back 20 periods using this yield rate of 2.5%, and then bring it back another 20 periods using this yield rate of 3%. So we would have 1,000 multiplied by a present value factor to the power of 20 using 0.025, and then you would multiply by another present value factor to the power of 20 using 0.03. Okay, so this is how you would calculate the price of this bond using your typical bond formula. Obviously, we had to change it a little bit. We had to split up the coupon portion into two annuity notations where one of them is multiplied by a present value factor, and then we needed to multiply our redemption value by two present value factors because we have two different yield rates for different periods of time. Okay, so this would certainly work. You could do this. You could calculate this in your BA2 Plus calculator. I'm not going to do that because there's actually an even easier way to calculate it in the calculator. I'm just showing you different ways of going about this solution. Here's what I'm going to do. We could actually use the TVM feature of the BA2 Plus calculator to make this calculation pretty quick. All right, but because there are two yield rates, there are two steps to this. So what we have to do is calculate the price at time 20 using this yield rate, and then whatever that price is would be the redemption value, so to say, for the rest of the payments or the rest of the coupons, and you would use that to calculate the price at time 0. All right, so let me show you how this is going to work. We're going to do two sets of TVM calculations. For the first one, we have TVM number 1. The future value, or the redemption value in this case, will be the $1,000. So we have 1,000. The payment amount is the coupon amount, so we'll make that 20. The number of coupons is 20. The total amount is 40, but just for those last 20 periods, which is where we are working, there are only 20 periods or 20 coupons. So N is 20. And then the interest rate I/Y is that 2.5% interest rate. So we'll do 2.5. Okay, remember you always put the interest rates into the calculator as a percentage, not as a decimal. So let's pull out the calculator here. First thing you want to do is make sure your time value money buttons are actually cleared out. So I'm going to do that here, hit second, future value, that clears it all out. The future value button has a second function of clear TVM. So just make sure that everything is ready to go. You have a blank slate. Anything you've previously done is not going to affect your new work. Okay, so let's put in all our values. We have 1,000. For the future value, we have $20 coupons, we have 20 of those coupons, and a 2.5% interest rate. Now what you want to do is compute the present value, and that will give you the price at time 20. All right, so I'm going to hit compute present value. Now, it comes out as negative, that's fine. You can just make it positive. That's the right answer. That is the price of this bond at time 20. And that is now actually going to act as our redemption value when we calculate the price at time 0 using the first 10 years of coupon payments. Okay, so this was our first TVM calculation. Now we're going to do a second one. We're going to have TVM number 2. And this time, the future value is not 1,000. It's going to be that present value we just calculated, which is $922 and about 5 cents. Our payment amount, or coupon payments, is still 20. The number of them is still 20, but now the interest rate changes. We don't have 2.5% for those first 10 years. We have 3%. So we're going to put in 3 this time. Okay? So clear out your TVM values in your calculator. So hit second future value. The actual future value for this calculation is already on my screen, so I'm just going to hit future value. We have $20 coupons, so put that in for the payment. We have 20 of them, and the interest rate is 3. Now we can hit compute present value, and there is the actual present value or price of this bond. Okay, so from this, we have now found that the price, or the book value at time 0, is equal to $808 and about 7 cents. All right, and that is the same thing that you would get if you calculated the price this way using the annuity notation and present value factors, but that would probably take you a little bit longer to do. But now that we have this price, we could use it to find the amount of principal in the 5th coupon, but that would admittedly take a bit of time. If you do want to do it that way, if you want to cycle through calculating interest, principal, book value, all the way up to the principal at time 5, I'll put the work up here on the screen, or the values that you would get for that. If you're interested, you can compare your work to my work. I really wouldn't recommend you do it that way because it's way too time consuming. Instead, here's how I would go about it in the calculator. Something to know about the BA2 Plus calculator is that you can do amortization for a bond right after you put in all the information for the price of the bond. So we just calculated the price of the bond. So what we can do now that we've done that is hit the second button and then PV, which has a second function of amort or amortization. So if you press that, you're going to go into the amortization menu, and we want to know the principal at time 5. So what you're going to do is set both of these P values at 5. So you go to time 5. So I'm going to hit 5, enter for P1. And then for P2, I'm also going to set it to 5. Basically, what those two values are for is setting a range of dates that you're interested in for the amortization schedule if you were to actually write it out. In this case, we just want to look at one specific period of time, so we don't want to look at a range of dates. We just want to look at time 5, so that's why I set both of those at 5. All right, but now if you go down, the balance, that would be the outstanding balance at time 5. We don't care about that. We want the principal, and there it is. It's negative 4.77. Now, remember that the problem does say the accumulation of discount for the 5th coupon, which means that the principal amount will probably be negative. In this case, it is. It's negative 4.77, but we just want the actual amount of discount. We don't really care about the sign of it. So we have found that PR5 is equal to 4.77. Technically, it's negative, but we don't really care about that for the solution to this problem. That is the final answer, and you could also find it here in the answer choices. It's answer choice C. So you would circle that or box it in. 4.77 is the answer to this problem. Okay, so overall, not too bad of a problem if you know your way around the BA2 Plus calculator. I included this problem in this video to show you how to calculate the price of a bond that has 2 yield rates, because that's something that could appear on an exam, and also to show you how to use the amortization function in the calculator when working with a bond, because you can find principal amounts, you can find interest amounts very quickly using that function. Okay, but with that, that's it for this problem. Let's move on to the next one. All right, so for problem 3, we have Rhonda repays a 40-year loan with annual payments starting 1 year from today. The first 30 payments are of $1,500 each, and the last 10 payments are of $700 each. It is known that the loan generates interest at an annual effective interest rate I, and the interest portion of the 21st payment is 3 times the interest portion of the 31st payment. Calculate the interest portion of the 31st payment. Okay, so in this problem, we are working with loan repayment or amortization. Not a bond this time. Last time we were working with a bond, but not this time. This is just a regular loan. And so let's write down everything we know about this loan. We know it's a 40-year loan, so N is equal to 40. The payments start 1 year from today, so that means that we are working with an annuity immediate. The payments are being made at the end of every period. We know that the first 30 payments are $1,500 each, and the last 10 are $700 each. And I'll try to make a note of that in a timeline rather than write down those payment amounts. But we also know that the loan generates interest at an annual effective interest rate I. We don't really know what that interest rate is, unfortunately, but we do know that it is represented by I. All right, so our interest rate here is I, but we don't know what it is. And then we're also told that the interest portion of the 21st payment is 3 times the interest portion of the 31st payment. So the way we can represent that as an equation is like this. We know that the interest at time 21, or I-21, is 3 times the amount of the interest at time 31. So that means it would be equal to 3 multiplied by I-31. Okay, that's what we know in this problem, and that's it, really. Our final goal here is to calculate the interest portion of the 31st payment, which would be I-31, but we don't really know how we're going to do that just yet. Note that in this problem, we don't know the amount of the loan, right? The original amount of the loan is unknown, and we don't know any principal amounts or any other book values. This is all the information we have to work with, aside from the actual payments that are being made. And something that's important to note here is that the payments are not level, right? In a lot of amortization problems, the payments are level. That's really what I focused on a lot in my amortization videos. In my financial mathematics series, I really focused in on level payment amortization and the formulas surrounding that, but you can also work with loans that have non-level payments and still be expected to solve the problem. And so in those instances, you kind of have to find some workarounds. You can't use the typical shortcut formulas that you can for level payments. You have to find a different way to do things. So to get a better idea of what we're going to do in this problem to solve it, I'm going to draw a timeline. Typically, I don't really draw timelines for amortization problems when the payments are level, but since they're not level in this case, a timeline will be helpful. So we have a total of 40 periods. So this right here will be time equals 0. This will be time equals 40. The first 30 payments are $1,500 each. So that means up to time 30, we have $1,500 payments. So starting at time 1, we would have $1,500, and we would continue to make those payments up to time 30. Then starting with time 31, we have those payments of $700 each. All right, so we have $700 all the way up to time 40. So keeping that in mind here, what can we do to calculate the amount of interest at time 31? Well, if you think about the different ways we know how to calculate interest at a specific time, we can't really use any shortcut formulas because, as I said earlier, we have non-level payments. So our really only other option of calculating that is by taking the outstanding balance at the previous year or the previous time and multiplying it by the interest rate, right? The interest at time 31 would be equal to the outstanding balance at time 30 multiplied by the interest rate, okay? That is true for any interest portion that you want to calculate. The interest at a specific time is equal to the previous outstanding balance times the interest rate. But we don't know either of these values, right? We don't know the interest rate, we don't know the outstanding balance at time 30, so clearly some more work is going to be involved here. But something that we do know, something that's helpful, is this equation that we wrote down here. We do know that I-21 is equal to 3 times I-31, so let's see if we can rewrite this in a way that maybe would be helpful. Because ultimately what we're going to have to do here is solve for the interest rate in some way. This is the only way we're going to be able to calculate I-31 most likely. We will need to know the outstanding balance at time 30, but in order to calculate that, we're going to need to know the interest rate, and we still need to know the interest rate to calculate the interest. So things aren't looking so good right now, but what I think we should do is rewrite this equation. We could rewrite I-21 and I-31 using an outstanding balance and interest rate, right? So let's do that. I already said that the interest at time 31 is equal to the outstanding balance at time 30 multiplied by the interest rate. And so the interest at time 21 would be equal to the outstanding balance at time 20 times the interest rate, right? The previous outstanding balance multiplied by the interest rate. So we would have OB20 multiplied by the interest rate on that side of the equation. But now notice that we have a common factor of I. I is on both sides of the equation, so we can cancel those out. Those are gone. Now we just have the outstanding balance at time 20 is equal to 3 times the outstanding balance at time 30. And now it seems like we didn't really get anywhere with that, right? We went from an equation that we don't know how to solve to another equation that we don't know how to solve. And so we really don't have any other choice but to try and set up how we would actually go about calculating these outstanding balances using these payments. And so let's try to do that. Let's see if that does anything for us. A lot of times in these hard FM problems, you just have to start setting up different equations, how you would calculate different things, and see if those equations can help you get to your final solution in some way. All right, so let's start by setting up how we would calculate the outstanding balance at time 20. And what the outstanding balance at time 20 represents is the loan balance after 20 payments. All right, so essentially it is the present value of the remaining payments, however much is still left to be paid. So the outstanding balance is valued at time 20. So let's say right here is time equals 20. That is where the outstanding balance at time 20 would be valued. So what we have to do here is take the present value of the remaining payments after time 20. That will calculate the outstanding balance at time 20. So how many payments are left? Well, time 20 is halfway through the loan, right? It's a 40-year loan, so there should be 20 payments. 10 of them are going to be of $1,500, and another 10 are going to be of $700, okay? From time 21 to time 30, we have 10 payments of $1,500, and then from time 31 to time 40, we have 10 payments of $700. So here's how we're going to calculate that. The outstanding balance at time 20 will be equal to the present value of 10 payments of $1,500. So we'll have $1,500 times A10 bracket I. We don't know what the interest rate is, but we can write I. That takes care of those 10 payments of $1,500. But then for the $700 payments, we will add 700 times A10 bracket I. That will calculate the present value of those 10 payments of $700, but be careful, it will value them at time 30, right? Annuity immediate notation values the present value of a set of payments one period before the first payment. So this notation values those 10 payments of $700 at time 30, so we need to bring them back another 10 years to be valued at time 20, which is where the outstanding balance at time 20 is valued. So we need to multiply by v to the power of 10. Okay, so that's the outstanding balance at time 20. Now let's set up how the outstanding balance at time 30 would be calculated. This one will be a little bit easier because the outstanding balance at time 30 is valued at time 30, right? So it will be valued right here, OB30. And to calculate that, we just need to take the present value of the remaining payments after time 30, which would just be 10 payments of $700. So OB30 would be equal to 700 times A10 bracket I. And that's it. Okay, so that is how we would calculate each of those outstanding balances. Now what I'm going to do is plug in those values into this equation because we know that OB20 is equal to 3 times OB30. So let's set that up. We'll start with OB20. So we're going to write in these two terms. We'll have 1,500 times A10 bracket I plus 700 times A10 bracket I times a present value factor to the power of 10 is equal to 3 times OB30, which is 700 times A10 bracket I. So we're multiplying by 700 A10 bracket I. Okay, so now remember what we're trying to do here. We want to try to solve for the interest rate so that we can then use it to help us find the actual interest portion in the 31st payment. And we'll also need that interest rate to calculate OB30. Okay, so let's see if we can do that here. There should be some way for us to isolate I. And the first thing I notice here, and hopefully you see it too, every single term in this equation has a common factor of that annuity notation, A10 bracket I. They're all the same, so we can cross those out. We can cancel them out. You can divide every single term by that annuity notation, and it's gone. So we'll cross out those notations, which makes this really easy, because now the only thing left in this equation that involves the interest rate is this present value factor. All right, this term just becomes 1,500. So we have 1,500 plus 700 times v to the power of 10. That's all that's left for that term. So we have 700 times v to the power of 10, and that will be equal to 3 times 700, which is 2,100. So we have 2,100. And now we can solve for v to the power of 10. First, we need to subtract 1,500 from both sides of the equation. 2,100 minus 1,500 is 600. So what we have here is 700 v to the power of 10 is equal to 600. Okay, now what we can do is use our BA2 plus calculator to solve for the interest rate. This is just a basic present value scenario here. So let's do that. In this case, 600 would be our present value. And by the way, before you do anything, make sure to clear out time value money. So hit second future value. $600 would be our present value. So we'll do 600, make that the present value. And then since we are going to be calculating the interest rate, we're going to be working with both a present value and a future value amount. One of them has to be negative. So $700 is our future value. It's what we're bringing back in time to get 600, right? It's being multiplied by present value factor. So I'm going to put in $700 as the future value, but also make it negative. All right, so we'll do 700, make it negative, put that in the future value. And then we have 10 periods, right? V is to the power of 10. So we'll do 10 for n, and then hit compute interest rate, and there it is, it's 1.55%. Okay, so we have found that the interest rate is equal to 1.55%. We used a calculator for that. Now, we still need to calculate the interest portion at time 31, but before we can do that, we need to know the outstanding balance at time 30, which we can do pretty easily now. We have that calculation right here. We just didn't know the interest rate before, but now we do. It's 1.55. So I'm going to store that in the 1 button. We'll come back to that if we need to, just so we don't lose the interest rate. But let's calculate this annuity. We have a present value equation here. So clear out your time value money buttons again. I'm going to hit second future value. Then we have 1.55 as our interest rate. So we'll hit I/Y. We have 10 payments, and the payments are of $700. So we have 700 as the payment amount, and then you want to hit compute present value, and there it is. That is the outstanding balance at time 30. We used the calculator and found that it's $6,437 and about 29 cents. There are more decimals there. But now what we can do is take that outstanding balance at time 30, multiply it by the interest rate, make sure to use it as a decimal, and that will calculate the interest at time 31. Okay, so I'm going to make the outstanding balance here positive, and I'm going to store that in the 2 button. Then what I'm going to do is recall 1. That's our interest rate, but as a percentage. So divide it by 100 to get the decimal, and then we'll multiply that by recall 2, which is where I put the outstanding balance, hit equals, and we get exactly $100, which is pretty crazy, but that's what it is. The interest at time 31 is $100. That is the final answer to this problem. And so looking at our answer choices, that would be answer choice A. And so I'll box that in. All right, let's take a look at our next problem. Okay, so for problem 4, we have a snack company must make payments of $2,000 at time t equals 2 and $4,000 at time t equals 4. Asset incomes of X at t equals 0 and Y at t equals 5 are needed so that the portfolio is Redington immunized at an annual effective interest rate of 5%. Find X plus Y. Okay, so in this problem, we are working with immunization, specifically Redington immunization. So immediately, as soon as you see that, you should be thinking of the conditions of Redington immunization and the types of equations that you can set up because of those conditions. Remember that Redington immunization has 3 conditions. The first one is that the present value of the assets is equal to the present value of the liabilities. The second is that the duration of the assets is equal to the duration of the liabilities, and you can use a Macaulay duration or a modified duration for that. And the third condition, which we may or may not have to use, sometimes you can get away without using it, but it's still good to check, and that is that the convexity of the assets is greater than the convexity of the liabilities. And that can be the Macaulay convexity or the modified convexity. In both cases, for duration and convexity, we will probably choose to work with the Macaulay versions because they're slightly easier to work with in most problems like this, where you're working with individual cash flows and there's not a whole lot of them. Okay, but what I like to do in immunization problems to help me set up the equations for those conditions is draw a timeline. So that's what I'm going to do here. We have a total of 5 time periods to account for. That's the farthest out that any of our assets or liabilities are valued. So I'll draw a timeline here and make this time equal 0 and this time equals 5. So this will be 1, 2, 3, and 4. Now I like to put the assets above the timeline and the liabilities below just to keep them separate. And the company must make payments of $2,000 at time 2 and $4,000 at time 4. Those are liabilities because the company has to make those payments. The payments are leaving the company, they're going out, so they're liabilities. So we have 2,000 at time 2 and 4,000 at time 4. Now for the assets, we have incomes of X at time 0 and Y at time 5. So we have X at time 0, Y at time 5. All right, and those are the assets that are needed so that the portfolio is Reddington immunized at an annual effective interest rate of 5%. So we know that the interest rate I is equal to 0.05 as a decimal, which is 5%. We want to find X plus Y, which means that we will need to find both X and Y, okay? In order to calculate X plus Y, we need to know what both of those values are individually. So that's going to be our goal here. We need to solve for those two values. And the way we're going to do that is by setting up the equations for those conditions of Reddington immunization. And so let's start with the first one. The present value of the assets must be equal to the present value of the liabilities. So let's start with the present value of the assets. X is already valued at time 0, so we're going to have X plus the present value of Y, which it's currently valued at time 5, so we need to bring it back 5 periods. So we'll have X plus Y times V to the power of 5. All right, and that's going to be equal to the present value of the liabilities, and we have two of them, 2,000 at time 2, 4,000 at time 4. The $2,000 needs to be brought back 2 periods, and the $4,000 needs to be brought back 4 periods. So we'll have 2,000 times V squared plus 4,000 times V to the power of 4. That's the first condition. We have set the present values equal to each other. Now, for immunization problems, you're always going to have to set up at least 2 equations. So let's just move right into the second condition and set the duration of the assets equal to the duration of the liabilities. And I'm going to use the Macaulay duration. Okay, we're going to have to set this up. One equation with 2 unknown values is not going to be enough. In order to solve for those values, we will need to use another equation. So let's set it up. Now, I am going to use a little trick here, or something that is going to make this process faster. Remember that when you calculate a Macaulay duration, the denominator of that calculation is the present value of the set of cash flows. So technically, we could ignore those denominators. I'll show you what I mean. This is just something that you want to take a note of when you're solving these problems on your own in the future. You don't have to go through as much work as I'm going to write down right now. You can actually skip some of this work to make the problem solving process quicker. But remember that for a Macaulay duration, you have a time-weighted present value divided by the present value. So for the assets, the denominator would just be X plus Y times V to the power of 5. But in the numerator, we would have the same present value, but where each cash flow is multiplied by the time at which they are made, or at which they are received, okay? That's how you calculate a Macaulay duration. Time-weighted present value divided by the present value. Now, for X, that payment is going to be received at time 0, so we would have 0 times the present value of that payment, which is just X, and then we're adding that to the present value of Y, but multiplied by the time at which it is received, which is 5. So we will have 5 times Y times V to the power of 5. And that will be equal to the Macaulay duration of the liabilities, which in the denominator, we're just going to have the present value, which is 2,000 times V squared plus 4,000 V to the power of 4. And in the numerator, we will also have the present value, but each of those cash flows will be multiplied by the time at which they are made, which is time 2 and time 4 respectively. So we have 2 times 2,000 V squared plus 4 times 4,000 V to the power of 4. All right, now here's the trick. Here's what I was referring to earlier. Since we already set the present values equal to each other, we're assuming that's true for these two equations. The denominators here of these Macaulay duration calculations is completely unnecessary. We already know that this is going to be equal to this. These are just the present values from earlier. So to make it easy on yourself, when you're doing immunization problems, you can just forget about the denominators in most cases. Don't forget that that's actually how you calculate a Macaulay duration, but in these equations, you can ignore the denominators. We're already assuming that they're equal. So I'm just going to erase both of those, and we're just going to work with the numerators for our second equation. All right, and now from these two equations, we should be able to solve for both x and y. The first thing I notice here is that we have 0 times x. That's going to be 0, so you can cross that out. And then in this equation, we should be able to solve for y. So that's what I'm going to do. we have 5y times v to the power of 5 is equal to 2 times 2,000 times v squared. So that will become 4,000 v squared. And we're adding that to 4 times 4,000 v to the power of 4. So we'll have 16,000 times v to the power of 4. Okay, now to solve for y, we want to divide both sides of the equation by 5v to the power of 5. So let's do that up here. Y will be equal to 4,000 v squared plus 16,000 v to the power of 4 divided by 5 times v to the power of 5. Now, we can do some simplification here to make putting this into our calculator a little bit easier. We can divide both 4,000 and 16,000 by 5. So 4,000 divided by 5 is 800. So y is equal to 800, and then v squared divided by v to the power of 5 would be v to the power of negative 3, right? You just subtract the exponents. 2 minus 5 is negative 3. And then you'd add that to 16,000 divided by 5. Let's do that. 16,000 divided by 5 is 3,200. So we have 3,200 times v to the power of 4 divided by v to the power of 5, which will be v to the power of negative 1. Okay, now, present value factors that have negative exponents are just the same as accumulation factors. And remember, we're using an interest rate of 0.05. So y is equal to 800 times 1.05 cubed plus 3,200 times 1.05. Okay, accumulation factors are the same as present value factors with negative exponents. Now we can plug this into our calculator pretty easily. Let's do that. Let's start with 800 times 1.05 cubed. I'm going to do 1.05 to the power of 3. There it is. And then multiply it by 800. And then I'm going to store that in the 1 button real quick, because then we want to take 3,200 times 1.05, hit equals, and then add that to recall 1. That's the other number that we calculated, hit equals, and there it is. We now know that y is equal to $4,286.10. Okay, now we can use that to help us calculate x. X is going to be equal to these two values, but then you're going to subtract y times v to the power of 5. So let's work on that next. We will have that x is equal to 2,000 times v squared plus 4,000 times v to the power of 4 minus y times v to the power of 5, which is 4,286.10 times v to the power of 5. Okay, now in each case, I'm just going to divide these cash flows by 1.05 to the power of the respective powers of those present value factors. So let's store the value of y in the 2 button, and then let's do this calculation. The way I'm going to do that quickly, since I have to take 1.05 to a power of 2 and 4 before I can divide those numbers by it, is actually to do the reverse. I'm going to take 1.05, square it, and then divide by 2,000 and take the reciprocal. All right, so divide by 2,000, take the reciprocal, and that's the first value. That's this part right here. I'm going to store that in the 4 button. Then we'll do it again, but for the 4,000 term, we'll have 1.05 to the power of 4, hit equals, divide it by 4,000, but that is the opposite of what we wanted to do, so hit the reciprocal button. There's the second value, store that in the 5 button, and then we're going to do the last one here. We have y times v to the power of 5. So we'll take 1.05 to the power of 5, hit equals, and we're going to divide it by recall 2, because that's where I stored my value for y, hit equals, then hit the reciprocal button, and there's our last value that we want to subtract from the addition of the other 2. So I'm going to make it negative, and then add recall 4, and add recall 5. There we go. That is our value of x. It's $1,746 and about 60 cents. All right, so x is equal to $1,746 and 60 cents. Now all we have to do to complete this problem is add x and y, and that will give us our final answer. So using x and using y, we will find that x plus y is equal to the number I currently have on my calculator screen plus recall 2, because that's where I stored y, hit equals, and there's our final answer. It's $6,032 and about 70 cents. That is the final answer to this problem. That is x plus y, and that corresponds to answer choice D. So I'll box that in. $6,033 would be the right answer, because if you round this up to the nearest dollar, you would get 6,033. Okay, if you wanted to, this would be a huge time waster, but if you want to do it just for the sake of doing it, you could check and see that Redington immunization is met here by looking at the third condition. If you calculated the Macaulay convexity of the assets and the Macaulay convexity of the liabilities, you would find that the Macaulay convexity of the assets is bigger than the Macaulay convexity of the liabilities. Okay, if you want to know what that looks like, I'll put the work for that up on the screen here for a couple seconds. Take a look at it, enjoy it. I'm not going to really explain it because it's not necessary for this problem. The problem already told us that the assets that were needed for Redington immunization are X and Y, so we're kind of assuming that Redington immunization is going to be met for those assets. We don't need to check that, especially because we weren't even asked to check it. We just needed to find X plus Y. That's it. Okay, so if you need to look at that work for convexity a little bit longer, feel free to pause the video. But with that, that's it for this problem. Let's move on to the next one. Okay, for our fifth problem, we have Wade is making plans to start a new business on January 1st of 2025. He plans to invest $90,000 immediately and $50,000 on January 1st of 2026 to kickstart his operations. Wade is anticipating his business to provide returns of $20,000 on January 1st of 2027 and increasing by 12% for each year up to and including January 1st of 2032. Find Wade's internal rate of return, assuming there are no cash flows after January 1st of 2032. Okay, so in this problem, we are going to be calculating an internal rate of return. So it's probably the case that we are going to be doing all of our calculations in the calculator. All right, but before we can break it out, before we can start using the calculator, we need to make a list of all of the cash flows that we are dealing with in this scenario. And the best way that I know to organize those cash flows or to see where they are valued and what their actual values are is to draw out a timeline. So that's what I'm going to do here. The first mark on our timeline, which would typically be time equals 0, I'm going to label with 2025, or in other words, the beginning of 2025. So that will be right here. And the last year that we're working with is 2032. So on the end here will be 2032. Okay, so then in between we have 2026, 27, 28, 29, 30, and 31. Now, Wade is going to invest $90,000 immediately. So since that is an investment, that is going to be a negative cash flow, or in other words, it is an outflow from the perspective of Wade's business. So at the beginning of 2025, we have negative 90,000. And then he's also going to make an investment of $50,000 on January 1st of 2026. That would be right here. So that's another outflow. It's another investment. So we have minus 50,000. Okay, now those are all the outflows that we are told about for Wade's business, but we're also told that he is anticipating his business to provide returns or inflows of $20,000 on January 1st of 2027. That will be right here. And then that's going to increase by 12% for each year up to and including the beginning of 2032. So at the beginning of 2027, there's an inflow of 20,000. I'm just going to write it like that, 20K. And then that's going to increase by 12% for the rest of these years. So we would multiply 20,000 by 1 plus this inflation rate, right? Technically, we have a geometric progression here. We're not going to calculate this like a geometric annuity, but that's the idea of what we're working with here. You could write that down if you wanted to. The inflation rate is 0.12 as a decimal. So to increase 20,000 by 12%, we would take 20,000 or 20K times 1.12. All right, then for every year after that, the 20,000 is going to increase by another 12%. So at 2029, you'll have 20K times 1.12 squared. At 2030, you'll have 20K times 1.12 cubed, and so on. And I'll fill that in right now. Okay, so you can see that at 2027, we had the 20,000. Then every year after that, we increase by another 12%. 1.12, 1.12 squared, 1.12 cubed, 1.12 to the power 4, and 1.12 to the power 5 in our final year of 2032. Now, for these cash flows, we want to find Wade's internal rate of return. And the best way, and probably the only way to do that, that's reasonable, is to use our financial calculator. Specifically, we're going to use the cash flow feature. And so to use it, you want to hit the CF button right here. That will take you to the cash flows menu. And then to make sure you're working with a blank slate and that there's no numbers in there already that will mess with your work, just hit second clear work and that will clear out the menu. All right, now CFO or CF0, that is the initial cash flow. For us, that is negative $90,000. That is at our time zero, so to say, for this scenario. So I'll put in 90,000, make it negative, and hit enter. Then we'll go down to C01. C01 will be our next cash flow, which is negative $50,000 at 2026. So just so you can kind of follow the pattern here, this was CFO, this is C01, this will be C02, C03, C04, C05, C06, and C07, just so that it's easier for you to follow along with what payments we are working with. All right, but for C01, we have negative 50,000, so I'll put in 50,000, make it negative, enter it. Now the frequency is 1, so we can leave that alone. F01, F02, and so on, those are all just referring to the frequencies of our payments, and all of them are only occurring once, all right? They're not repeating cash flows. They're going to be different each time. So just leave that one alone. We'll go down to C02, which is 20,000. So we'll do 20,000, hit enter, go down. The frequency is still 1. That's never going to change for this problem. We'll go down to C03. Now things get a little bit more difficult. We have to start including the increase of 12% each time. So what I'm going to do is take 1.12, multiply it by 20,000, hit equals, and then hit enter. That is our cash flow at time 3. Now let's go down to cash flow 4. This time 1.12 will be squared. So we'll do 1.12 squared multiplied by 20,000, hit equals, hit enter. That's our 4th cash flow. Let's go down to cash flow 5. This time 1.12 is cubed. So we have 1.12 to the power of 3, hit equals, then multiply by 20,000, then hit enter, go down to C06, or our 6th cash flow. This time 1.12 will be to the power of 4, so we have 1.12 to the power of 4, hit equals, then multiply by 20,000, hit equals, then hit enter, go down to C07, which is our final cash flow, where 1.12 will be to the power of 5. So we have 1.12 to the power of 5, hit equals, multiply by 20,000, one more time, and then hit enter, and we're good to go. F07, the frequency, should still be 1. Now that we have entered all our cash flows, what we want to do is hit the IRR button, and then hit compute. And it takes a little while, as you just saw, but now we've got our final answer of 3.39%, or really you could round that up to 3.4%. All right, so using the BA2+, I'll write that down here, using BA2+, we found that the IRR is equal to 3.3957%, which would be the same as 3.4%. So our final answer would be answer C. That is the correct answer choice for this problem. For problem 6, we have Tiffany deposited $500 in a savings account that earned interest at a force of interest of Y% per year. After X years, her deposit accumulated to $700. Stella also deposited $500 in a savings account, but her account earned interest at a force of interest of X% per year. How much was in Stella's account after 3Y years? Okay, so in this problem, we're dealing with 2 different savings accounts, one for Tiffany and one for Stella. So we want to try to keep that information separate, but they will be tied together because they're dealing with the same unknown variables, that being X and Y, right? Notice that Tiffany's account has a force of interest of Y%, and then after X years, she has accumulated $700, but Stella's account earns a force of interest of X%, and then we want to know how much she has after 3Y years. So those variables of X and Y are part of both of those accounts. So we're probably going to be setting up two different equations and then using those together to solve for x and y, or something like that, that will then allow us to calculate how much is in Stella's account after 3y years. All right, so let's organize our information here. Let's start with Tiffany. For Tiffany, she's a force of interest of y% per year. So her force of interest delta is going to be equal to y times 0.01. The reason I'm writing that is because y would be a percentage, but as a decimal, you would want to multiply that by 0.01 to get the actual decimal. That's the same as dividing by 100, right? If you have a 5% interest rate, if you multiply 5 by 0.01, that gets you 0.05. So that would be the decimal equivalent of that 5% rate. That's all I'm doing here. We're multiplying that value of y by 0.01. Okay, so that's her force of interest. Now let's write down Stella's. She is a force of interest of x%, so that will be x times 0.01. All right, now let's set up some equations involving their deposits. For Tiffany, she deposited $500 in her savings account, and after x years, her deposit accumulated to $700. So $700 is her future value. That's going to be equal to that $500 she deposited but accumulated for X years using this force of interest. And since this force of interest is a constant force of interest, right, even though we don't know what y is, we are allowed to assume that that is probably just some constant number. It's not going to be a value of time, or it's not going to be t. So this is not a force of interest dependent on time. It's a constant force of interest. So the accumulation factor for a constant force of interest is just e raised to the power of the number of years multiplied by that force of interest. So we have x amount of years. So we have e to the power of x multiplied by the force of interest, which is y times 0.01. Okay, so that's our equation for Tiffany. Now for Stella, she also deposits $500, but we don't know what her future value is. We actually want to calculate that after 3y years. So I'm just going to represent that like this. The future value of Stella's account is equal to her $500 accumulated for those 3y years using her constant force of interest, x times 0.01. So we'll have e to the power of 3y multiplied by x times 0.01. Okay, and just to reiterate where this factor of e raised to this power is coming from, in general, when you're working with a force of interest, the accumulation factor looks like this. You have e to the power of an integral from 0 to n of your force of interest times dt. But if your force of interest is not dependent on time, if it's constant, you're just taking the integral of a constant, which will be that constant times the variable of integration, which would be t. And so then you'd evaluate it at n, subtract the evaluation of 0, and every time you will just end up with n times delta, or delta times n. Okay, so when you have a constant force of interest, this is your accumulation factor. If you make the exponent negative, then you have a present value factor. All right, so just a little review there. Thought I'd talk about that to make sure that we are on the same page. But now back to our problem. We want to calculate this future value, but in order to do that, it looks like we need to know what x and y are. And so let's try to solve for one of those and see what happens. Over here, we have an equation for Tiffany where we have both x and y, and everything else in the equation is known. So let's just try to solve for one of those variables. I'm going to choose to solve for x and see what happens. Whatever x is equal to, I'm just going to plug that into this equation and see how it works out. It may work out, we may get some nice cancellations and calculating the future value will go smoothly, or we might encounter a problem and we'll have to figure out some other way to go about this problem. But that's what I'm going to try to do first. All right, because this is all we have to work with. There is really nothing else that we could do here. There's no other equations we could write out. This is all we have to work with, so let's work with it. Okay, so to solve for x, the first thing I'm going to do is divide both sides by 500. 700 divided by 500 is 7/5. So we will have 7/5 equal to e to the power of x times y times 0.01. Now, to get rid of e, I'm going to take the natural log of both sides of the equation. And by the way, 7 divided by 5 is the same as 1.4. That's what 7 divided by 5 as a decimal would be. So we have the natural log of 1.4 equal to the natural log of e to the power of x times y times 0.01, but e and the natural log are inverse functions. They cancel each other out, so we're just going to be left with what is in the exponent. So we have x times y times 0.01. Now, to solve for x, we just have to divide both sides by y times 0.01. So I'll do that right here. We will find that x is equal to the natural log of 1.4 divided by y times 0.01. All right, and so now that we have solved for x, let's plug this in for x in this equation and just see what happens. Maybe something will cancel out, like I said earlier, or maybe not. We're going to find out. The future value is equal to 500 times e to the power of 3y, and then we're going to multiply by x, which, as we just found, is a natural log of 1.4 divided by y times 0.01. So I'll write in the natural log of 1.4 divided by y times 0.01. And then don't forget, we're still multiplying by 0.01 right here. Okay? And just as I sort of predicted, we have some nice cancellation that's going to occur here. Notice that we have y in the numerator and denominator. Those are going to cancel out. And we have 0.01 in the numerator and denominator as well. So all we're left with here is that the future value is equal to 500 times e to the power of 3 times the natural log of 1.4. And if you wanted to, you could plug this into your calculator as it is, but I'm going to make it easier for myself. We can simplify this. E and the natural log will cancel each other out, but before we can do that, we need to move this constant multiple from out front of the natural log function to be inside. I'm going to use one of the properties of logarithms, which is that you can move a constant being multiplied by the logarithm to be the power of whatever is inside the logarithm. Okay, that is a property of logarithms that I'm going to use here. So the future value will be equal to 500 times e to the power of the natural log of 1.4 cubed. But then e and the natural log will cancel out. So this just becomes 500 times 1.4 cubed. Okay, and so now what we're left over with here is a pretty simple calculation. I don't think I need to show you how to do that in the calculator. I'm just going to give you the answer here. 1.4 cubed is 2.744, and multiplying that by 500 will get you the final answer that the future value after 3y years for Stella's account is $1,372. That is the final answer to this problem, and that would be answer choice D. So I will box that in here. Okay? Next up, for problem 7, we have Samson has a $200,000 30-year mortgage with a 36% annual nominal interest rate, convertible monthly. His original plan is to pay it off by contributing an amount X each month. However, after making these payments for 10 years, Samson decides to double his monthly payments to 2x in order to pay off the mortgage faster. How many years will Samson shave off the initial 30-year term, assuming a drop payment for the final fractional payment? All right, so in this problem, it looks like we are working with amortization. We have a 30-year mortgage or a 30-year loan, and Samson is making monthly payments to pay it off. Now, he initially is going to pay X every month to pay it off, but after a certain point, he's going to switch to payments of 2X. And so what we're probably going to want to do here is, for one thing, find the amount X of those payments, if at all possible, and determine how much of Samson's $200,000 loan is left over after he makes those payments for 10 years. Because after that, he technically has a second loan. It's not really another loan, but from the perspective of our calculations, there is going to be a new balance that he then tries to pay off with these 2X payments. Okay, if that sounded kind of confusing, don't worry. I'm going to explain it as we go through the work here. First thing I'm going to do is just write down all the numbers that we've been given, everything we know about this loan. We know that the original amount of the loan is $200,000. So the loan amount L is equal to 200,000, and that would also be the outstanding balance at time zero, just to remind you that that is the case. And there's a total of 30 years, but he's making the payments monthly, right? Contributing an amount X each month. That's his original plan. So N is equal to 30 times 12, 12 months for each year. So that gives us a total of 360 months. Okay, now for the interest rate, the mortgage has a 36% annual nominal interest rate convertible monthly. So we've been given this. We know that I convertible 12 times per year is equal to 0.36. So the monthly effective interest rate, which is what we are going to need to use here because we have monthly payments, J sub 12 is equal to 0.36 divided by 12, right? You just take the nominal rate divided by the number of times it's convertible in a year to get the equivalent effective rate for that same period type, that being months, and we will find that that monthly effective interest rate is 0.03. Okay, so that's everything that we've been given. Now, let's start with the initial plan, because his initial plan is to pay off that loan of $200,000 with X every month. So that would be 360 payments of X. So for the original plan, we would have $200,000 as the present value of 360 payments of X. So you would have X times A 360 bracket that monthly effective interest rate, which is 0.03. Okay, and we needed a monthly effective interest rate for that because these payments are monthly payments. So when you use annuity notation, the interest rate must match the payment cycle. So we're good here. Monthly payments, monthly interest rate, and the value of N is also measured in terms of months. Okay, so now this is not too bad. We can actually solve for X right away. We can use a financial calculator to solve for the payment pretty quickly. So let's do that. First thing you want to do is make sure to clear out your time value money buttons in your calculator. So hit second future value. Then we have a $200,000 loan or $200,000 present value. So we'll do 200,000 as the present value. If you wanted to, you can make that negative, then your payment amount would come out positive, but I don't really care about that. The payment will come out negative, but I know that it's positive. It doesn't really bother me. But then we have 360 of those payments. So we have 360 as N, and the interest rate is 3%. Compute the payment amount, and there it is. It's about $6,000. $6,000.14 if we want to be really specific. All right, so from the original plan, we now know that Samson was planning to make payments of X every month for 30 years, which would come out to be about $6,000.14 every time. However, that's not what he sticks to, right? After making these payments for 10 years, he switches to payments of 2X every month. All right, and then what we want to find here is how many years Samson will shave off the initial 30-year term, assuming a drop payment for the final fractional payment. So what we need to do here is figure out how much was left in the loan when he switches to those payments of 2X, and then figure out how long it's going to take for those payments of 2X to pay off the loan. And then once we know that value of N, we can figure out how many years he shaved off. Okay, so the first thing we need to find is the balance of his loan after he makes these monthly payments of X for 10 years. So in other words, we're looking for the outstanding balance after 10 years, which, if we're working in terms of months, is 120 months. So we need to find OB 120. So OB 120 would just be equal to the present value of the remaining payments. Okay, so we're still working with the initial plan here. We're still trying to figure out how much money is left over after he makes 120 payments of X, which we now know is a little bit over 6,000. And the way we can calculate that is by taking that value of X, 6,000.14, and multiplying it by the annuity notation, A, and then the number of payments left over, which would be 240, and then bracket the interest rate, 0.03. Now, I got 240 by subtracting the value for the outstanding balance that we want to find from the total amount of payments. All right, so 360 minus 120 gets you 240. Okay, we're just taking the present value of the remaining payments after he makes those payments for 10 years, and then that outstanding balance will be what he still needs to pay off with those remaining payments of 2X every month. Okay, so let's calculate this outstanding balance in our calculator. I'm going to make that payment amount positive, and then I'll store it in the 1 button just in case something happens. I still have it. I can recall it and not need to do that calculation again from earlier. But then what you want to do is clear out your time value money buttons. So I'll hit second future value, clear it all out. This is now our payment amount, so I'll make that the payment. We have 240 payments and a 3% interest rate. Compute present value. And there's our outstanding balance after 120 months or after 10 years. The outstanding balance at time 120 is $199,838 and about 78 cents. Now, if you're looking at the original loan amount, that's not great, is it? It looks like Samson barely paid anything off, but as we know, eventually it will get paid off after he makes a total of 360 payments of X, but he wants to do it quicker, okay? So that's why after 10 years, he's going to switch to payments of 2X. Now, let's set up what that new plan would look like, where this outstanding balance is the new loan balance, right? This is how much he has left after 10 years, and so this is how much needs to be paid off by those payments of 2X every month. So let's set up that equation now. For the new plan, this is our new loan balance, or present value. We'll have 199,838.78, and that will be equal to payments of 2X. And so 2X would be 2 times 6,000.14, which would be 12,000.28. I'll actually do that calculation in the calculator. I believe I saved the amount of X, so I'll just take that and multiply it by 2. But then that will be multiplied by an annuity notation for an N number of months. We don't know what that's going to be, but that's what we want to solve for. We don't know how long it's going to take for Samson to pay off this loan now that he's doubling his payment amounts, but that's what we want to determine. All right, but then don't forget that the interest rate is 0.03. We're still using the same monthly interest rate. Okay, so we can actually solve for N pretty quickly here. We can just use our calculator. We have all the values we need to do so. So let's go to the calculator here. On the screen right now, I still have that outstanding balance. I'm going to make it positive. And just so I don't lose that value in case something were to happen, I'm going to store it in the To button. And then before I use the TVM buttons, I want to make sure to clear them out. So I'm going to hit second future value. Now let's make this the present value. We don't know what N is, so leave that alone, but we do have a 3% interest rate. And then remember, I stored the amount of X in the 1 button, so I'll hit recall 1. There's our value of X at 6,000. I'll multiply it by 2, and then make that the payment amount. But in this case, I will need to make it negative. You could have done that for the present value as well. Just make sure that either the payment or the present value is negative. Otherwise, you won't be able to calculate N. Okay? When you're trying to find N, or the interest rate for an annuity, either the present value or the payments needs to be entered in as negative. One of those two things must be negative, and then the other obviously needs to be positive. Okay? But that's our payment amount, and then we can hit compute N, and we get a value of 23.4. Now you might be wondering, what about the drop payment? Didn't we forget about the drop payment? And no, not really. Yes, it's true that Samson will be making a drop payment for the final fractional payment, but we didn't need to include that in our calculation here because now we can see where it would come in. And let me explain. We got a fractional amount of time here, right? We got 23.42. What that's telling us is that 23.42 of these 2X payments would need to be made to pay off this loan, or that's how many months it would take to pay off this remaining balance of the loan. Okay, so really what's happening is we're making 23 of those payments and then a smaller fractional payment, which would be the drop payment. Okay, so you can just sort of see where the drop payment comes into play through the value of N here. We didn't actually need to include a drop payment in our calculation. We didn't have to do plus and then some value times a present value factor. That would just make things way too complicated. We don't need that. We can see where that drop payment comes in through that value of N. Okay, so what we found here is that N is equal to 23.42, which means we're making 23 of these payments plus an additional fractional payment, which would be for time 24. Okay, you're going to make 23 of these payments plus a fractional payment at time 24 or in a 24th month to pay off this balance. So really, N is a total of 24. That's not what N would be for this calculation. That would be a little bit overkill, but that's how many total periods it's going to take for Samson to pay off this outstanding balance or what's remaining in his loan. Now, 24 months is the same as 2 years, right? So that turns out to be 2 years, but that's not the final answer. Don't box in 2. That's how long it's going to take him to pay off the loan after 10 years have already passed, right? So after 10 years, he switched to payments of 2X, and then after that, it only took 2 more years to pay off the loan. So really, it's going to take a total of 2 plus 10 years to pay off the loan, which is 12. That's how long it takes him to pay it off, but that's also not the right answer because we were asked how many years will Samson shave off the initial 30-year term. So the answer is not 12, it's going to be 30 minus 12, okay? Originally, he was going to pay it off in 30 years, but instead he paid it off in 12, so the difference is how much time he shaved off. That is where we get our final answer of 18. All right, so I'll do that up here. Time shaved off is 30 minus 12, which equals 18. Okay, that is the final answer to this problem, so I'll box it in here. That is answer choice E. For problem 8, we have Nate receives $750,000 for his retirement. He invests $750,000 minus X in an annual payment 15-year annuity immediate and X in an annual payment perpetuity immediate. Nate's total payments received per year during the first 15 years are twice as large as those received thereafter. Given that the annual effective rate of interest is 8%, find X. Okay, so in this problem, it looks like we're just working with some different annuities. In fact, we actually have a perpetuity as well. And so let's write down everything we know about the annuity and perpetuity in this problem. We know that Nate is going to invest $750,000 minus X in an annual payment 15-year annuity immediate. So let's write that down. $750,000 minus X would be the present value of that annuity. So you would have $750,000 minus X equal to the present value of that 15-year annuity immediate. Now, we're not told what the payment amounts are for that annuity. We don't know the level payment. So I'm just going to call it Y. And so we'll be taking the present value of 15 of those payments of Y. And the interest rate is 8%. And that is an annual effective rate of interest. So we're good. That matches the payment cycle. So I'll put in 0.08. Okay, so that's what we know about the annuity immediate. But then we also know that Nate is going to invest X in an annual payment perpetuity immediate. So now that's an annuity that pays payments forever. But once again, we don't know what those payment amounts are. And we also can't just assume that they will be the same as this annuity. So he's investing X. That's the present value of the perpetuity, but it would be equal to how you would actually calculate that present value, which would be taking the amount of the payments, which I'm going to call Z, and dividing it by the interest rate, which is 0.08. Okay, so right now we have 3 different variables. We have X, Y, and Z, but we only have 2 equations, which makes things kind of difficult. We're not going to be able to solve for all 3 of them without another equation. That's just algebraically how that's going to work. If you have 3 variables, you need 3 equations to solve for all of them. You can't solve for all 3 with only 2 unless you're given some other piece of information. So we either need another equation or something is going to have to help us out here. And so this is where I want to draw attention to something else that we were told in this problem, that Nate's total payments received per year during the first 15 years are twice as large as those received thereafter. Now to get a visual here, let's draw a timeline. I want to show you exactly what that's telling us. So if this is our timeline, he does have a perpetuity, so this is going to go on forever. Right here is time equals 0, but starting with time equals 1, he's going to receive payments from his annuity immediate. He's going to get Y every year, and he's also going to get payments of Z from his perpetuity. But now the annuity ends after 15 years. So after time 1, you have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But then starting with time 16 and thereafter, I'll just label this as time 15. Starting with time 16 and afterwards, Nate's only getting payments from the perpetuity, all right? So keep that in mind, but at every moment in time, up till time 15, he's getting a payment of Y from that annuity immediate and a payment of Z from that perpetuity. All right, so I filled that in here. You can now see where all of those payments would be on the timeline. But what this is telling us in the problem is that the total payments received per year during the first 15 years are twice as large as those received after. So up to time 15, the amount he's receiving every year, which would just be Y and Z, those are equal to twice the amount of what he's receiving after 15 years, which after 15 years, he's just going to be receiving payments of z, right? So this is what we know. We know that y plus z must be equal to 2 times z, right? The amount he receives per year during the first 15 years, that's y plus z, are twice as large as those received after. And so he's only receiving z after time 15, so if you multiply it by 2, that means that those two things should be the same. But now here's the punchline. If you subtract z right here from both sides of the equation, this just becomes z. And what we find is that y is equal to z. In other words, the payments for the annuity are the same as the payments for the perpetuity. All right, so that's pretty important. You can't just make that assumption. If they didn't tell us this, if they didn't tell us that the payments received each year during the first 15 years were twice as large as those thereafter, we couldn't make this assumption. Some people will try to do that when they have a lot of unknown values, but you have to find a way to back it up, and that's what we did right here. We have now shown that y is equal to z. So we can now get rid of one of our 3 unknown variables in these 2 equations, so we'll just have 2 unknown variables and 2 equations, so we'll be able to solve for both of them. Or really, we just want to solve for x. We don't really need to know what y is for the answer to this problem, but we may still need to find it in order to figure out what x is. Okay, but now, since we know that y equals z, I'm just going to get rid of z. I'm going to erase that and just put in y. And since we know that x is equal to y divided by 0.08, we can plug that in right here and solve for y, and then we'll be able to use that to solve for x. At least the way that I'm going to go about this. You could solve for y in this equation and then plug it in here to solve for x, but I think it's going to be easier to just plug this in for x here and then solve for y and use it for this calculation. All right, so let's do that. Plugging this expression in for x will give us this. We will have 750,000 minus y divided by 0.08 is equal to y times a 15 bracket 0.08, and 1 divided by 0.08 is 12.5. So I'm just going to rewrite that like this. We'll have 750,000 minus 12.5 times y. That's just an easier way to write y divided by 0.08. But then we want to set that equal to y multiplied by this annuity notation, which we are now going to have to find the value of in our financial calculator, okay? We'll just pretend as though the payments are $1, and then whatever that present value turns out to be, that will be the coefficient or number being multiplied by y, which will then allow us to solve for y by combining our like terms. Okay, so let's do that. Let's pull out our calculator. Before I plug any of our information in, be sure to clear out the time value money buttons, hit second future value. Then, to calculate this present value, we want to put in $1 payments. So we'll do 1 as the payment amount. Then we have 15 of those payments, so 15 is n, and an 8% interest rate, so 8 is I/y. Then hit compute present value. Now that should be positive. I just put the payments in as positive, so the present value comes out as negative, but make it positive, and that would be what's being multiplied by y. We have y times 8.559 and some more decimals. And so we have like terms here. We have y being multiplied by a constant value. So if we add 12.5y to both sides of the equation, in other words, if I just do plus 12.5 in the calculator, we get 21.059 times y. So we'll have 750,000 is equal to 21.059 times y. And now all we have to do to solve for y is divide both sides by 21.059. In other words, we need to divide 750,000 by that value. And I'm going to do it in the reverse here. Since I already have 21.059 on my calculator screen, I'm going to divide it by 750,000 and then hit the reciprocal button, which is the same thing as what we want to do. Okay, I'm just creating a fraction and then flipping the fraction to get the right value. So let's divide by 750,000. Hit equals, then hit the reciprocal button, and there's our answer. Y is equal to $35,613 and some more decimals. And now if we take that value divided by 0.08, that will give us x. All right, so let's do that. Take your value, divide it by 0.08, and there's x. We now know that x is equal to $445,167 and about 71 cents. That is the final answer to this problem. And so looking at our answer choices here, this lines up with answer choice B, 445,170. Okay, all of these answers are rounded up to the nearest tens place, not the ones place. So we can round this up, okay? But B is the correct answer to this problem. Okay, so next up is problem 9. We have a loan is amortized over 6 years with monthly payments at an annual nominal interest rate of 6% compounded monthly. The first payment is $1,000 and will be paid 1 month from the date of the loan. Each succeeding monthly payment will be 3% lower than the prior payment. Calculate the outstanding balance immediately after the 50th payment is made. Okay, so just from reading the problem, I can already tell that we are working with loan amortization, right? The first sentence makes that pretty obvious. A loan is amortized over 6 years with monthly payments. That's good. We know what we're working with. And it's also pretty clear what our end goal is. We want to calculate the outstanding balance for that loan immediately after the 50th payment is made. All right, and something that's important to note here is that this is not a level payment loan, right? This loan has payments that will decrease by 3% every time they're made, right? Each succeeding monthly payment after the initial payment of $1,000 will be 3% lower than the prior payment. That is describing a geometric progression, or in other words, this loan is being paid off by payments that decrease geometrically. We are working with a geometric annuity within a loan amortization problem, which is fine. That's nothing that we can't do, but it is important for you to realize that and not calculate the wrong outstanding balance, because the way we're going to go about this is different than if the payments were level. So before we do anything, before we try to calculate anything, let's write down everything we know and also draw out a timeline that's going to help us figure out how we're going to calculate that outstanding balance. The first thing I notice is that this loan is being amortized over 6 years with monthly payments. So our value of n will be equal to 6 years times 12 months for each year, which gives us a total of 72 months or 72 payments that will be made to repay the loan. Then we're also told that the annual nominal interest rate is 6% compounded monthly. So that means that I compounded monthly is equal to 0.06. And we're going to need a monthly effective interest rate since we know that our payments are being made monthly. So let's just convert that right away. We know that j sub 12 will be equal to 0.06 divided by 12, which is equal to 0.005, right? You take that nominal rate divided by 12 to get the monthly effective rate. And we can only do that because this is a nominal rate convertible 12 times per year. If it was convertible quarterly, we would have to do some extra work to get the monthly effective rate. We wouldn't just be able to divide by 12. Since these numbers both match, 12 and 12, we're good to go. We can divide that by 12 to get the effective rate. Okay? Now, the initial payment is $1,000, but then after that, it's going to change. So we do have an inflation rate here. Specifically, it's going to be negative 3% because the payments are decreasing by 3%. It says each succeeding monthly payment will be 3% lower, not higher than the prior payment. So that means it's decreasing. So our inflation rate here, R, is equal to negative 0.03. Okay, so that's basically everything we know, but now let's draw out a timeline. Let's get a better picture of this loan and its payments. We'll start with time equals 0 and end with time equals 72, right? That's the total number of periods that we're working with. The first payment at time equals 1, we are told that the first payment is going to be paid 1 month from the date of the loan. So the date of the loan would be time 0, meaning the first payment is at time 1. That's just telling us that we're working with an annuity immediate. The payments are being made at the end of every month or the end of every period. So we have 1,000 at time 1, but then at time 2, it's going to decrease by 3%. So we would multiply 1,000 by 1 plus the inflation rate, which would be negative 0.03, and that would just become 0.97. All right, so I'm going to erase this. The factor that we're going to be multiplying by each payment to decrease it by 3% is 0.97. So the payment at time 2 would be 1,000 times 0.97. And if you went to time 3, you would have 1,000 times 0.97 squared, and you could continue on that pattern. But now, remember where we want to calculate our outstanding balance. We want to calculate the outstanding balance immediately after the 50th payment is made. So that would be made at time 50. And when you calculate an outstanding balance, what you're doing is calculating the remaining amount of the loan that needs to be paid off. In other words, it's the present value of the remaining payments that have yet to be paid. So if we skip some time here in our timeline, and I mean a lot of time, we're going from time 3 to time 50, what would the payment amount be at time 50? Well, it would be 1,000, but decreased by 3%. How many times? Well, looking at the pattern for our previous payments, at time 2, we multiplied by 0.97 to the first power, and then at time 3, we multiplied by 0.97 squared. So it looks like whatever the amount of time is, the power of 0.97 is 1 less. So 1,000 will be multiplied by 0.97 to the power of 49 at time 50. Okay, but then at time 51, we will have 1,000 times 0.97 to the power of 50, and that would continue on till the last payment at time 72, which will be 1,000 times 0.97 to the power of 71, right? The value of time minus 1 will be the power of that 0.97. Okay, so when we want to calculate this outstanding balance after the 50th payment, what we're doing is calculating the value of the loan at time 50. We want to know the present value of the remaining payments from time 51 to time 72. That is what we're going to calculate here. We want to value all of those payments at time 50, not time 0, time 50, because that's where the outstanding balance at time 50 or after the 50th payment would be valued. Okay, so really here, we are still calculating a present value of a geometric annuity. That's really all we're doing here. It just looks a little bit different because we're calculating a specific outstanding balance rather than the present value of an entire set of payments forming a geometric progression. Okay, so let's write out some of the terms here. For OB50, or the outstanding balance at time 50, here's how we would calculate that. We'd start with the payment at time 51, but we would need to bring it back 1 period or 1 month. So we'd have 1,000 times 0.97 to the power of 50, but then you need to multiply that by a present value factor to the first power. And then the next payment would be 1,000 times 0.97 to the power of 51. You would need to multiply that by v squared. You would have to bring it back 2 periods to be valued at time 50. And that pattern would continue on till the last payment at time 72, where you'd have 1,000 times 0.97 to the power of 71 times v to the power of 22. Right, that's how many periods are between time 50 and time 72. You would need to bring this payment back 22 periods, and that would get you to time 50. Okay, so these are the stream of payments that we're working with. And if you've watched my lesson video from my financial mathematics series on how to calculate geometric annuities, then the process that I'm going to go through here should look pretty familiar. The first thing that's important to do is pull out the first term from all of those terms, because it's going to be a common factor of all of them, right? This can be found in every single one of those terms. So if we pull this out, our outstanding balance will be equal to 1,000 times 0.97 to the power of 50 times v multiplied by 1 plus 0.97 times v plus 0.97 squared times v squared, all the way up to 0.97 to the power of 21 times v to the power of 21. Right? If you pull the first term out of the first term, you're just going to be left with 1. Then if you pull it out of this, you'll be left with 1 factor of 0.97 and 1 present value factor. And that pattern will continue. You'll have both of them squared, then both of them cubed, all the way up to the last term where you have both of them to the power of 21. Okay? And what you're left with here is a geometric series. You could rewrite these terms as a geometric series. That's what I'm going to do next. The outstanding balance would be equal to 1,000 times 0.97 to the power of 50 times v times a geometric sum, or a geometric series, from k equals 0 to 21 of 0.97 times v. And that would be to the power of k, right? You take that quantity to the power of 0, you get 1. Then you take them both to the power of 1 to get this term, then 2, all the way up to 21. All right, and then if you take the sum of that geometric series, remember that it's equal to 1 minus the inside of the geometric series to the power of n plus 1. and then you divide by 1 minus the inside. All right, let me just write that down in case you haven't seen it in a while. If you have a geometric series from k equals 0 to n of some value a to the power of k, the sum is equal to 1 minus a to the power of n plus 1 divided by 1 minus a. Okay, that's what I'm using here. So in this case, a is 0.97 times v. So the outstanding balance will be equal to 1,000 times 0.97 to the power of 50 times v times 1 minus 0.97 times v to the power of 22. We add 1 to that power of n, right? It's not 21, it's 22. And then you divide by 1 minus 0.97 times v. Okay, so that right there is actually how you would calculate the outstanding balance at time 50. But this would be pretty complicated to put into your calculator. So if you've watched my video on how to use a financial calculator for different topics in financial mathematics, then you might be aware of a little trick that makes geometric annuities a little bit easier to calculate in the BA2+. It can seem a little complicated at first, but if you just memorize one extra formula, it's not so bad. Let me show you what I'm talking about. What this trick boils down to is that we can recognize this quantity right here to be in the same form as the formula for the present value of an annuity due. You have 1 minus a present value factor, so to say, to the power of 22 divided by 1 minus that same factor. It doesn't matter that they don't look like present value factors. We can sort of treat them like one and solve for an interest rate. I'm not going to explain everything about this process. If you want to learn about it from scratch, you can check out my financial calculator guide video. But this is what this calculation will become. We'll have 1,000 times 0.97 to the power of 50 times v times the present value of an annuity due for 22 periods. It's the same value that we have right here, using an interest rate m, where m is equal to 1 plus the interest rate divided by 1 plus the inflation rate minus 1. Okay, that's the extra formula that you have to remember. That's what I was referring to earlier. So in this case, I would be 0.005, R is negative 0.03. So this would be equal to 1.005 divided by 0.97 minus 1. And whatever the result of that is will be the interest rate for this annuity due. That makes this calculation a whole lot easier. Okay, but where this formula comes from is that we're just setting the inside of this quantity equal to a present value factor, where the interest rate for that present value factor is m. Okay, if you're curious where that comes from and you haven't watched my other video, that's the origin of this little formula here. You end up solving for m, and this is what you get. But now let's actually work on calculating this outstanding balance. Let's pull out our financial calculator. First thing we want to do is calculate that interest rate m. So we'll take 1.005, divide it by 0.97, hit equals, and then subtract 1. That's our interest rate, but as a decimal. And remember, when you use the financial calculator for calculating annuities, you want to work with your interest rates as percentages, so you want to multiply that by 100. Okay, so it's a 3.6% interest rate, essentially. That's what we're working with for this annuity due. All right, so I'm going to store that in the 7 button in case we need to recall it at some point. I think we will, but for now, let's focus on calculating this right here. So we're going to have an annuity due with payments of this amount right here. I'm going to calculate that first, but before we do any of that, we need to switch our calculator from end mode to begin mode so that we actually calculate the present value of an annuity due and not an annuity immediate. So to do that, you want to hit second payment and then second enter, and that will set it to BGN, and then you can hit second quit to go back to calculating. All right, and now you can see at the top here it says BGN, so we are good to go. We are now going to be calculating annuity dues instead of annuity immediates. All right, and now you can see it's a good thing I stored that interest rate because now it's not on my screen anymore. We'll pull it out when we need it. But let's just start by calculating the payment amount for our annuity. This present value factor V is still using this interest rate of 0.005. Don't get confused. That's not using M. Just the actual annuity due formula is using that interest rate of M. Okay, and I did forget to write that down. It's about 0.036 as a decimal. There are some more decimals there, but that's what we found. All right, but anyway, let's calculate this payment amount here. Before we do anything, you should clear out your time value money buttons again. So I'll hit second future value to clear that out. Then let's calculate that payment. We'll take 0.97 to the power of 50, multiply it by 1,000, And then to take care of the present value factor, we just need to divide by 1 plus the interest rate. So divide by 1.005. So we'll hit divide by 1.005, hit enter, or equals, sorry, not enter, equals. And there's the payment amount. So let's make that the payment. We have 22 of those payments. And our interest rate M, I stored in the 7 button, I believe. So I'll hit recall 7, and there it is. So let's make that the interest rate, and then hit compute present value. And there it is. That right there is the outstanding balance at time 50, or the outstanding balance immediately after the 50th payment for this loan. Okay, so we have found that OB50 is equal to $3,373 and about 88 cents. All right, there are some more decimals there, but that's the final answer. And so if you round up to the nearest dollar, you can see that this matches up with answer choice A of 3,374. Okay, now before we move on to the next problem, I just want to give you a little tip here. You don't have to go through all the steps I went through here. I was just being a little bit cautious about how I explain the solution here. So really, if you're used to working with geometric annuities, you could skip a little bit of this work. Once you know what that first term is, when you're valuing all your payments at the time where you want them to be valued, once you know what that first term is, just take that first term and multiply it by an annuity due formula, where your value of n is the number of payments that you need to take the present value of, and the interest rate is 1 plus I divided by 1 plus R minus 1. Okay, that's a really quick way to calculate a present value of a geometric annuity. I don't really tell you to do that in any of my other videos, but I'm kind of telling you here, when you're taking an exam and your time is limited, you probably want to skip some of these in-between steps unless you really need to write them out for your own sanity. I think you can go without them to save yourself some time. Okay, so that's my little tip for test-taking strategies when it comes to geometric annuities. But that's it for this problem. Let's move on to the next one. Here we have problem 10. A liability consists of a payment of $3,000 to be paid 6 months from now and a payment of $2,500 to be paid 1 year from now. The only investments available are 6-month zero-coupon bonds with a 4.5% yield rate and 1-year par value bonds with 7% coupons and a 5.2% yield rate. Assuming all yielding coupon rates are nominal rates convertible semi-annually, calculate the total cost of a portfolio that exactly matches the liability cash flows. Okay, so the last part of this problem gives away what type of FM problem we're working with. We're told to calculate the total cost of a portfolio that exactly matches the liability cash flows. That tells us that we're working with asset liability exact matching. All right, so in those types of problems, remember that the value of assets and liabilities at each moment in time must be equal. That is essentially what we're being told here. Okay, so you want to keep that in mind. Now, in these types of problems, drawing a timeline is pretty important, so let's get that out of the way here. Let's draw one. It doesn't need to be a huge timeline, because if you look at our assets and liabilities, they all take place within a 1-year span, right? We have a liability of $3,000 to be paid in 6 months, and another of $2,500 to be paid 1 year from now, and then both of the investments or assets take place within a year as well. We have 6-month zero-coupon bonds and 1-year par value bonds. So we can draw a pretty small timeline here. I'll draw it like this. This will be time equals 0. This will be time equals 1, which would be the same as 6 months. So I'll just write 6 months. And then this will be time equals 2 or 1 year. Okay, we're going to be working with semi-annual periods. Since 6 months was mentioned, that's the same as a semi-annual period, right? Half of a year is 6 months. So let's label our assets and liabilities. We have assets above the timeline and liabilities below it. We have liabilities of $3,000 to be paid 6 months from now. So that would be at time 1. So I'll write in 3,000, and then 2,500 at 1 year from now. So we have 2,500. Okay, and now for the assets, this is where it can get a little bit tricky if you're not careful. We have 6-month zero-coupon bonds with a 4.5% yield rate. And what kind of cash flows do we get from a zero-coupon bond? Well, As the name implies, we don't get any coupons, so we're just going to get the redemption value at the end of maturity, which in this case would be at the end of 6 months. So at the end of 6 months, at time 1, you will get the redemption value for that 0 coupon bond. I'm just going to call that C, all right? C will be the redemption value of that 0 coupon bond. That will be valued at time 1. All right, so that's it for the 6-month 0 coupon bonds. And by the way, that is plural, so this value of C would represent the total amount of redemption value received from all of those 0 coupon bonds. Just like when we work with the next asset here of 1-year par value bonds, we will assume that our coupon amount and redemption amount will include all of the coupons and all of the redemption values for all of the bonds that may be purchased to exactly match the liabilities. We don't know how many are actually being bought, and it doesn't seem like that really matters for this problem because we're not asked about that at all. Okay, but for a regular 1-year par value bond, we know it's paying semi-annual coupons because we're told that all yield and coupon rates are nominal rates convertible semi-annually. So the coupons are definitely being paid semi-annually. So we're going to get a coupon at time 1 and at time 2, along with the redemption value being returned at time 2 or the end of maturity for those 1-year bonds. Okay, so I really didn't give myself enough space to write that in. Let me move this timeline down a little bit. At time 1, we're going to get some amount of coupons that I'll represent with F times R. All right, in other words, you can view that as F is the total amount of face value from all of those 1-year bonds, and then you're multiplying it by R to get the total amount of coupons. All right, so you'd get that at time 1. You would also get that at time 2, but you'd also get the return of the redemption value, which in this problem we can assume is the same as the face value because we're not told otherwise. So you'll also get F. So at time 2, F plus F times R is what is being received from that investment or that bond. So that is our asset at time 2. Okay, so just as a reminder, I'm saying that F is the face value of the 1-year bonds, and I didn't really color code the coupon rate, but we'll just say that it's R, and I'll just write over them there. Now we've set up our timeline, and so let's talk about how we're actually going to solve this problem now. Remember that we want to calculate the total cost of a portfolio that exactly matches the liability cash flows. So that could actually be done 2 different ways. Since the assets and liabilities are being exactly matched, both of their present values should be the same. So you could calculate the cost of the portfolio by either calculating the present value of the assets or the present value of the liabilities. However, in this case, only one of those ways is going to be viable. It's not really going to be possible for us to calculate the present value of the liabilities because the way that you would go about that is by using the appropriate yield rate from the assets that match each of those liabilities at each moment in time. In other words, what I'm saying here is that usually you would use the 4.5% yield rate for the 6-month 0 coupon bond for this liability to take it back to time 0. That's the rate that you would use. And you would use the 5.2% for the second liability at time 2 because that's where it would be matched to that 1-year bond. However, you can't do that because they are not exclusively matched, is how I like to think about it, or how I like to say it. Yes, at time 2, this liability is being exactly matched to this singular asset, but at time 1, we have a mixture of assets. We have our 0 coupon bond and the 1-year regular bond that both are using 2 different yield rates. So you can't just pick one of those yield rates to use for this liability to value it at time 0, if that makes sense, right? That liability is being matched to a combination of assets that are coming from 2 different sources that have 2 different yield rates. So you can't just use one yield rate on that liability to bring it back to time 0 to calculate the cost. That's not going to work. So what we have to do instead here is calculate the cost of the portfolio by calculating the present value of the assets. But you might be thinking, how are we going to do that? We don't know what F or C are. We know what the coupon rate is, I just haven't written it down. The coupon rate is 7%, but divided by 2 because it's convertible semi-annually. In fact, let me do that right now. R is equal to 0.07 divided by 2, which is equal to 0.035. That's the coupon rate. However, we don't know what F and C are, but we can find them. All we have to do is take advantage of the fact that we know that the assets and liabilities are being exactly matched, meaning that 3,000 should be equal to the sum of the assets at time 1 and 2,500 should be equal to this asset right here. So let's create those two equations. We'll have 3,000 is equal to F times R, and R is 0.035, plus C, and then we have 2,500 is equal to F plus F times R. If you pull F out of those two terms, you'll have F multiplied by 1 plus the coupon rate, which will be 1.035. Okay, so now we could solve for F here. If you divide both sides of this equation by 1.035, we have 2,500 divided by 1.035. That will give us $2,415 and about 46 cents. So that's our value of F. We get that from this equation. F is equal to 2,415.46. And then now that we know that, we can plug that into this equation to solve for C. We can multiply it by 0.035 and subtract it from 3,000. So let's do that. Let's multiply by 0.035, it equals, and we want to subtract that from 3,000. By the way, that's also the amount of the coupon. So I'm just going to write that to the side here. We now know that F times R is equal to 84.54 and some more decimals. But anyway, we want to subtract that from 3,000. So I'm just going to hit minus 3,000 and then hit plus or minus, and there we go. That's our value of C. So I'll put that right here. C is equal to $2,915 and about 46 cents. And now that we know what both F and C are, we can calculate the present value of all of our assets. We just have to make sure to use the appropriate yield rates. All right, so here's what we're going to do. We want to value all of our assets at time 0. So let's start with the redemption value C of 2,915.46. That asset comes from the 0 coupon bonds, which is a 4.5% yield rate. And remember that that is convertible semi-annually, so we need to divide that by 2. So the actual yield rate for this 0 coupon bond would be equal to 0.045 divided by 2, which is 0.0225. Okay, so that's that yield rate. Let's set that part up. Remember that we were trying to calculate the cost, and in this case, we are doing that by taking the present value of the assets. Let's actually calculate it here. Our redemption value C of 2,915.46 will be brought back one period by multiplying by present value factor using that yield rate of 0.0225. That will bring it back one period. And then we need to do the same thing for this coupon amount, which we know is 84.54. We need to bring that back one period, but use the yield rate for the bond that actually pays those coupons. All right, so we have a 5.2% yield rate for that bond. So let's do that on the side here. We have another yield rate J, which is 0.052 divided by 2, and that will be equal to 0.026. Okay, that rate that we were given is convertible semi-annually, so we needed to divide it by 2 to get the effective yield rate. Okay, so now we're going to add the present value of a coupon payment from time 1. So we'll have 84.54 multiplied by V to the first power using 0.026. And then we want to add that to the present value of this F and this coupon payment, which we know is going to be equal to 2,500, right? You could add the coupon payment to the actual face value and you will get 2,500 because the assets and liabilities are going to be exactly matched at each moment in time. Okay, so the total assets at time 1 is equal to 3,000 and the total assets at time 2 is equal to 2,500. But since there's no 0 coupon bond values at that time, it's just the face value and coupon from those 1-year bonds, we know that that has to be equal to 2,500. So we'll have 2,500 brought back 2 periods using that 2.6% yield rate. So we're multiplying by V squared using 0.026. All right, and that's it. Now we just have to plug all this into our calculator to calculate the cost of this portfolio that exactly matches the liability cash flows. So let's start with the redemption value here. We're multiplying it by a present value factor using this yield rate. So really we just need to divide it by 1.0225. So I already have that value on my calculator here. So we'll hit divide by 1.0225. It equals. That part we're going to be adding to these other values later on, so I'm just going to store that in the 1 button for now. Now, let's calculate the present value of the coupon payment. You could include more decimals if you like. I think we'll be fine if we just use 2 of them here. So I'm going to do 84.54 divided by 1.026. All right, that's the same as multiplying by the present value factor of 1 divided by 1 plus the interest rate. We just divide by 1 plus that interest rate. So that's the present value of that coupon. So I'm going to store that in the 2 button. And now let's work on the last one here, and then we'll add everything together. We need to take 2,500 back 2 years using a 2.6% interest rate. So here's how I'm going to do that. I'm going to take 1.026, square it. That is what would be in the denominator. But if we divide it by 2,500 and then hit the reciprocal button, that will get us what we want. So I'm going to hit divide by 2,500, then hit the reciprocal button, and that would be 2,500 divided by 1.026 squared. Okay, so that's the present value of that last term. Now let's add it to the other 2 things that we calculated. So hit plus recall 2 plus recall 1. That's where I had all those other values stored. And there's our final answer. We have now just found that the cost of this portfolio is $5,308 and about 60 cents. Okay, that's the final answer. You could compare it to your answer choices here and see that all of them are rounded up to the tens place. So answer choice D would be the right answer here. 5,308 would be rounded up to 5,310. All right, so D is the right answer choice. For problem 11, we have Ava owns 3 bonds with the same effective annual yield rate, I. The first bond is a perpetual bond. The second is an N-year zero coupon bond whose modified convexity is X. The third is a 2N-year zero coupon bond whose modified convexity is 3X. If the ratio of the modified convexities for the perpetual bond to the 2N-year zero coupon bond is 104, find the common yield rate I of Ava's bonds, assuming that that yield rate is greater than 0. All right, so in this problem, we've been given a lot of information. We know that we're working with 3 different bonds, and we've been given some different information about those bonds. In particular, we know that we're going to be working with the modified convexities of all 3 of these bonds. Right, we're told what the modified convexities are in terms of this variable x for both the N-year zero coupon bond and the 2N-year zero coupon bond, and then we're told something about the ratio of the modified convexities between the perpetual bond and the 2N-year zero coupon bond, that being that the ratio is 104. Now, before we go any further here, if you've never seen the phrase perpetual bond before, all that means is that it's a bond that pays coupons forever. It's essentially a perpetuity, but where the payments every period forever are the coupon payments. All right, there will be no return of the redemption value at the end of maturity because there is no end of maturity. It's a perpetual bond. It goes on forever. All right, so keep that in mind as we move forward here in this problem, because that's going to be important as we begin to set up some equations that will allow us to solve this problem. And as of right now, it's not entirely clear how we're going to be able to solve for that common yield rate. But as I already pointed out, we know that we are working with modified convexities for all 3 bonds, so I think that's a good place to start. We should just set up how we would calculate the modified convexity for each one of these 3 bonds. And remember, the definition of the modified convexity is that it's equal to the second derivative of the price function or present value function for a set of cash flows divided by the original price function or present value function for those cash flows. So what we're going to have to do to set up the modified convexity for each bond is represent each bond with a present value or price function, and then take the derivative twice and set up the modified convexity calculation using those 2 functions. All right, so we have a bit of work to do here, so let's get started. Let's begin by looking at the perpetual bond. For the perpetual, what would our present value or price function look like? Well, P of I would be equal to the present value of all of the coupons, okay? Now remember what I said earlier, a perpetual bond is basically the same thing as a perpetuity, but where the payment amount is the amount of the coupons, and we don't know what that is, right? We don't know the face value, we don't know the coupon rate for this perpetual bond, so we'll just represent that with F and R. All right, so we'll have a coupon amount, F times R, divided by the yield rate for that bond, which we know all three bonds have the same common yield rate of I, so we'll just divide that by I, and that would represent the present value of the perpetual bond. That's it. It's just the amount of each coupon divided by the yield rate. But another way that we could write that to make it easier for us to take a derivative, because we do have to do that here, let's just write it like this. We'll have F times R times I to the power of negative 1. Just move that I to the numerator and make its exponent negative. Now, what we need to do is take the derivative of this function twice. So let's start with the first derivative. P prime of I will be equal to the derivative of this function with respect to I. So it looks like we need to use the power rule for derivatives. We'll multiply the exponent down and subtract 1 from the exponent. So we'll have negative F times R times I to the power of negative 2. Now we need to take the derivative again. So let's do P double prime of I. We need that second derivative for the modified convexity calculation. If you take the derivative again, you need to multiply negative 2 down and then subtract 1 from that exponent. So we'll have positive 2 times F times R times I to the power of negative 3. Okay, now let's set up the modified convexity for this perpetual bond. The modified convexity will be equal to the second derivative of the price function divided by the original price function. So we'll have 2 times F times R times I to the power of negative 3 divided by F times R times I to the power of negative 1. Okay, so notice that there's some things that cancel out here. For one thing, it doesn't matter what the amount of the coupon is because it's in the numerator and denominator of this calculation for the modified convexity. So we can cancel those out. F times R is just going to disappear from that expression. And then we have I to the power of negative 3 divided by I to the power of negative 1. We can subtract exponents here. Negative 3 minus negative 1 is the same as negative 3 plus 1. So we'll just be left with I to the power of negative 2. Okay, so the modified convexity here is equal to 2 times I to the power of negative 2. That's pretty nice. That's the modified convexity of the perpetual bond. So that takes care of the first bond. We still have 2 more to work with here. So let's start working on those. Next, we'll look at the N-year zero coupon bond. We know that its modified convexity is x, so we'll get to that later. For now, we need to set up a price function for that zero coupon bond and then take its derivative twice. Now remember, the way you calculate the price of a zero coupon bond is by multiplying the redemption value C by a present value factor to the power of the number of years, or the number of periods. So in this case, that would be C times V to the power of N. But since we want to work explicitly in terms of I with a price function, I'm going to write out that present value factor in terms of I. Remember that a present value factor would be the same as 1 plus I to the power of negative whatever the exponent of that present value factor was. In this case, it's just N. All right, so this is our price function for an N-year zero coupon bond. If we take the derivative of that, we will need to use the chain rule technically because we have this whole quantity of 1 plus I raised to a power of negative N. But since the derivative of that inside function would just be 1, right? The derivative of 1 is 0 and the derivative of I to the first power is 1. We don't need to worry about the chain rule. We can just use the power rule for derivatives on this quantity and we'll be fine. Okay, so the first derivative, P prime of I, will be equal to negative N times C times 1 plus I to the power of negative N minus 1. All right, we multiplied negative N down, and then we subtracted 1 from that exponent. Now let's do that again. We need to take the second derivative of the price function. We'll multiply the exponent down again, and subtract another 1 from that exponent. So we're going to have negative N times negative N minus 1 times C times 1 plus I to the power of negative N minus 2. Okay, we multiplied that quantity down of negative N minus 1 and subtracted another 1 from the exponent. So now instead of negative N minus 1, we have negative N minus 2. Now let's set up the modified convexity for the N-year zero coupon bond. Remember that we know that the modified convexity is x, so I'm going to say that x is equal to the second derivative of the price function divided by the original price function. So we have negative N times negative N minus 1 times C times 1 plus I to the power of negative N minus 2. Okay, and I think I forgot to mention this earlier, but obviously we don't know what the redemption value is. That's why I just represented it with C. If we did know what it was, we could plug that in if we wanted to, but as you're going to see in just a little bit, it actually doesn't matter what that value of C is. It's going to get canceled out, because if we divide by the original price function, we'll have C times 1 plus I to the power of negative n, and now you can see that C is in the numerator and denominator, so we can cancel it out, as well as a factor of 1 plus I to the power of negative n. That's also in the numerator and denominator. We can cross those out, and we'll just be left with a quantity of 1 plus I to the power of negative 2. Don't forget about that. That didn't disappear, right? Just to make sure it's clear what I'm doing here, this would be the same as 1 plus I to the power of negative n times 1 plus I to the power of negative 2. We just crossed out this part of that factor, so now we're just going to be left with this part. So here is what we have left. The modified convexity x is equal to negative n times negative n minus 1. I'm going to distribute that negative n through that quantity. You'll have positive n squared plus n, and that will be multiplied by that quantity of 1 plus I to the power of negative 2. Okay, so that right there would be the modified convexity for the n-year bond. X is equal to this expression. All right, so now let's move on to the last bond, the 2n-year zero coupon bond. For the 2n-year zero coupon bond, we know that its modified convexity is 3x, so keep that in mind when we go to set that up. But first we need to come up with our price function. The price function, P of I, will be equal to the redemption value of that zero coupon bond multiplied by a present value factor to the power of 2n, right? That's the number of periods or the number of years for that zero coupon bond. But now I'm going to write it out explicitly in terms of I, so we're multiplying by 1 plus I to the power of negative 2n. All right, now let's take the derivative. P prime of I is equal to negative 2n times C times 1 plus I to the power of negative 2n minus 1. We just used the power rule for derivatives again. Remember that we can ignore the chain rule since the derivative of that inside function is just 1. So negative 2n was multiplied down, and we subtracted 1 from that exponent. Now take the derivative again. P double prime of I will be equal to negative 2n times negative 2n minus 1 times C times 1 plus I to the power of negative 2n minus 2. We multiplied that exponent down, and then we subtracted 1 from that exponent. Now let's set up the modified convexity. We know that it's equal to 3x for this 2n-year bond. So we'll have 3x equal to the second derivative of the price function divided by the original price function. So we'll have negative 2n times negative 2n minus 1 times C times 1 plus I to the power of negative 2n minus 2. And then we were dividing by C times 1 plus I to the power of negative 2n. Now, just like with the n-year zero coupon bond, we didn't know what the redemption value of the 2n-year zero coupon bond is, but it doesn't matter. It's going to get canceled out. It's in both the numerator and denominator of this calculation. So we can cross that out, and we also have a factor of 1 plus I to the power of negative 2n that we can cancel out. So I'll cross those out. Just don't forget that we do still have a factor of 1 plus I to the power of negative 2. So let's simplify the modified convexity here. We will be left with this. We'll have 3x is equal to negative 2n times negative 2n minus 1. I'm going to distribute that through this quantity. So we will have positive 4n squared plus 2n, and that quantity will be multiplied by 1 plus I to the power of negative 2. All right. And that's our setup. We are now done with setting up the modified convexity equations for all three of these bonds that Ava owns. Now what our goal should be is to try to solve for I, right? That's our end goal here. We want to find the common yield rate I of Ava's bonds. Now we can try to do that with these three equations. But you might have noticed there's one piece of information we haven't used yet, and that is the fact that the ratio of the modified convexities for the perpetual bond to the 2n-year zero coupon bond is 104. So let's take care of that. We actually can create another equation that's going to help us solve for I as well. And that part is actually very important, so we got to set this up. They didn't just give us that piece of information for fun. We were given that for a reason. So I hope it's okay at this point. I'm going to clear out all of this work except for the modified convexities. If you need to reference this work, feel free to just go back in the video to look at it. But I'm going to clear it out now so I have some space to work with. here are our three modified convexities, but for this ratio that we've been given, we only need to work with the perpetual and the 2N-year zero coupon bond. Specifically, the ratio of the modified convexities for the perpetual bond to the 2N-year zero coupon bond is 104. So that looks like this. The ratio of the modified convexity of the perpetual bond, which is 2I to the power of negative 2, to the 2N-year zero coupon bond, which means that will be in the denominator. We'll just call that 3x, since we actually know what it's equal to. That right there will be equal to 104. That's what it's telling us. The ratio of this convexity for the perpetual bond to this convexity for the 2N-year zero coupon bond is 104. Now, we'll come back to this equation in a little bit. I'm not really sure what we can do with this at the current moment in time, but something that I do notice here that could be nice to work with is that for the two modified convexities of the zero coupon bonds, we know that one is equal to x and the other is equal to 3x. So if we just divide both sides of this equation by 3, we can set these two things equal to each other because then they'll both be equal to x. All right, so I'm just going to erase this 3 here and then just multiply by 1/3, or in other words, we're dividing by 3. And now both of these convexities are equal to x, so let's set them equal to each other and see if we can solve for I or possibly n. Solving for n might be helpful as well, but let's see what happens. I'm just trying to find some way to solve for some unknown variable because currently we have 3 of them. We have I, n, and x. We don't know what any of them are equal to, so let's try to solve for one of them. That's kind of my hope here. Since both of these are equal to x, let's set them equal to each other. We'll have n squared plus n times 1 plus I to the power of negative 2 is equal to 1/3 times 4n squared plus 2n times 1 plus I to the power of negative 2. Now, something that's really nice here is both sides of the equation have a common factor of 1 plus I to the power of negative 2. So those cancel out. We can just cross those out. You could divide both sides of the equation by that factor, and it would be gone. And then I'm going to multiply both sides by 3 to get rid of that fraction of 1/3. So we'll have 3 times n squared plus n is equal to 4n squared plus 2n. And now at this point, the only unknown variable we have is n, so we should be able to solve for it here. Let's see if we can do that algebraically. If I distribute this 3 through this quantity, we'll have 3n squared plus 3n is equal to 4n squared plus 2n, and then combining our like terms might be helpful here. Let's subtract these two terms over to the other side. 4n squared minus 3n squared will just be n squared, and then 2n minus 3n will be negative n. So we'll have 0 is equal to n squared minus n. And then we can solve for the two values of n here. If you pull out the common factor of n from these two terms, I'll do that up here. We'll have 0 is equal to n times n minus 1. And then we can solve for our two values of n. We know that n will be equal to 0, and then n minus 1 will be equal to 0. And so you have n equals 0, n minus 1 equals 0, which means that n equals 1. So what we found here are two values of n that could potentially be the right value of n for this scenario, but I think we can reasonably make the conclusion that the right answer is not n equals 0, because that would mean that those zero coupon bonds don't exist. There is no time associated with them, right? If n equals 0, there's no periods, and so therefore there's no bond. So we can kind of rule that one out. N equals 0 is not the right value of n. We want to work with n equals 1. So now that we know that, that's kind of nice. We should now be able to use that to help us express x in terms of one unknown variable, not two, right? This one's a little bit easier to work with than this one. So if we plug 1 in for each of these n's, we'll have a very nice expression for x that maybe we can combine with this expression to solve for I. So let's work on that. Since we know that n equals 1, let's plug it in for these two n's, and we'll find that x is equal to 1 squared plus 1 times 1 plus I to the power of negative 2. Now 1 squared is 1, plus 1 will be 2. So this just becomes x is equal to 2 times 1 plus I to the power of negative 2. So now we have an expression for x that is in terms of just I. And over here, we could also solve for x and then replace that with what we found it's equal to, and then everything will be in terms of I in that equation, and so then we can try to solve for I, okay? So there's a lot of algebra involved here, but it's nothing that we can't do. So let's try to solve for x here. Let's multiply both sides of the equation by 3x. So I'll move that up here. we'll have 2I to the power of negative 2 is equal to 104 times 3x. 104 times 3 is 312, so we have 312 times x. And then rather than solving for x here, let's just plug this expression right here in for x. Okay, that's what I'm going to do at this point. We're just going to put that x right there. And here's the result. We'll have 2I to the power of negative 2 is equal to 312 times 2 times 1 plus I to the power of negative 2. Now we have a common factor of 2 on both sides of the equation, so we can cross those out. Those are gone. And then we're left with I to the power of negative 2 times 312 times 1 plus I to the power of negative 2. All right, now in order to solve for I, we probably want to have those exponents be positive. So in order to do that, I'm going to do this. Note that we would have 1 divided by I squared is equal to 312 times 1 divided by 1 plus I to the power of 2. And so if you multiplied both sides of the equation by I squared and 1 plus I squared, this is what you should get. You'll have 1 plus I squared is equal to 312 times I squared. Okay, so we just multiplied both sides of the equation by what is in the denominators of those two fractions, and now we have a nice expression where both of those exponents are positive, and we should be able to solve for I at this point. We just have to expand this squared quantity, and then we'll have a nice quadratic expression to work with. So let's do that next. If we continue our work up here, let's square this quantity. I'm going to do it the quick way, square the first term, so we'll get 1. Then multiply the two terms together, and then multiply them by 2. So 1 times I is I, times 2 will give us 2I. And then square the last term. I squared is, of course, I squared. And that will be equal to 312 times I squared. All right, now, if we subtract all these terms over to the other side of the equation, we'll have 0 is equal to 311 I squared minus 2I minus 1. All right. 312 I squared minus I squared is 311 I squared, and then these two terms become negative because we're moving them to the other side. Now at this point, we have a quadratic expression that we could factor. However, I don't really know how to factor that, so I'm going to use the quadratic formula to do it as fast as possible. All right, so remember, the coefficient of the squared term is a, the coefficient of the middle term is b, and the constant value is c. And then the quadratic formula tells us that I is equal to negative b, so that would be positive 2, plus or minus the square root of b squared, so negative 2 squared is 4, minus 4 times a, which is 311, times c, which is negative 1, all divided by 2 times a, so 2 times 311. Okay, now we need to pull out our calculator to do this. Let's start with the square root portion. We have 4 minus 4 times 311 times negative 1. So we're going to have 311, but it will be negative because we're multiplying it by negative 1. Then multiply it by 4, and then that's going to be subtracted from 4. So technically we would be adding it to 4 because we're subtracting a negative number. So make it positive and then add 4. And there's the value under the square root. So now what we need to do is take the square root of that. So let's press the square root button. There's the square root of it. I'm going to store that in the 1 button so we can pull it out later to do our second answer. But let's start with the one where we add 2, and then we'll divide by 622. So we'll add 2, and then let's divide by 622. And there's our first answer. That's probably going to be the right one. In general, when you end up using the quadratic formula in an FM problem to solve for an interest rate, usually when you add the part under the square root, you get the right answer. When you subtract, you'll find that you get a negative interest rate, which is not what we want in this case. But the first answer we get is that I is equal to about 6%, so 6.00%. That does seem to be one of our answer choices. So we could probably stop here if we wanted to, but just to show you that the other interest rate is negative and it's not the right answer, I'll do that here as well. So let me clear my work. Let's recall 1. That's the value underneath the square root. We want to subtract that from 2, so I'll make it negative and then add 2. That's now the numerator. If you divide it by 622, there's the other answer that you could get for I, but it's about negative 5.36%, which we don't want that. I will write it down. I is also equal to negative 5.36%, but that is not going to be the right answer. You don't want a negative interest rate in this case. We know that it's greater than 0, or at least that's what the problem is telling us. And in general, if they don't tell you that, you can assume that you want the positive interest rate. Okay, but that's the final answer here. I is equal to 6%, and so we can choose the right answer choice. It is answer choice C. 6% is the interest rate, or the common yield rate, I should say, for all three of the bonds that Ava owns. The perpetual bond, the N-year bond, and the 2 N-year bond, which actually, since we know what the value of N is, it would just be a 1-year bond and a 2-year bond. Okay, let's move on to the next problem. For problem 12, we have Chester makes a deposit into an account that earns compound interest. In 7 years, his deposit is worth $8,000, and in 12 years, it is worth $9,500. Find the amount of Chester's deposit. Okay, so this seems like a pretty simple problem. There's not a whole lot of information to work with here, so our options are limited in terms of what we can do. I think what might be helpful here is to draw a timeline of what is happening in this problem. So I'm going to draw a timeline here real quick. We know that he makes a deposit today, and in 7 years it's worth $8,000, and in 12 years it's worth $9,500 or $9,500. So if this is time 0, then the end will be time equals 12, and then let's say that time 7 is right about here. Okay, I'm not going to write in all the middle dates. That's not really necessary in this case. We know that Chester makes some deposit of X that we want to find, and it is worth $8,000 in 7 years and $9,500 in 12 years. So from this information, we can make a couple equations here. We know that if we accumulate X for 7 years, so if we multiply by 1 plus I to the power of 7, that will get us to that value of 8,000, right? We know that to be true. After 7 years, using compound interest, Chester's deposit of X will become 8,000, but then in 12 years, we know it will be 9,500. So we can make another equation here that X accumulated for 12 years using that compound interest rate will be equal to 9,500. So now we have two equations and also two unknown variables, that being X and I, and so algebraically, we should be able to solve for both of those variables. Specifically, in this case, we do want to know the amount of Chester's deposit, but if we have to solve for I first before we can solve for X, that's fine, as long as we can find X. Okay, and in this case, it looks like the easiest thing for us to do is to solve for X in both of these equations and then set them equal to each other. Solving for I might be a little bit of a pain right now, so let's not try to do that. We can just divide both sides of these equations by their respective accumulation factors. And doing that will just move them to the other side of the equation and turn them into present value factors, right? So we'll have X is equal to 8,000 times V to the power of 7, and X is equal to 9,500 times V to the power of 12, okay? Those present value factors would just be equal to 1 divided by those accumulation factors, so I'm just writing it like this to make it simpler. Now, since these are both equal to X, let's set them equal to each other. We'll have 8,000 times V to the power of 7 is equal to 9,500 times V to the power of 12. Now what I'm going to do is divide both sides of the equation by 8,000 and divide both sides by V to the power of 12. So if we do that, we'll have V to the power of 7 divided by V to the power of 12 is equal to 9,500 divided by 8,000. And then V to the power of 7 divided by V to the power of 12 will become V to the power of negative 5. So let's do that here. We'll have V to the power of negative 5 is equal to 9,500 divided by 8,000. And I'm just going to reduce those by a factor of 100. So we'll have 95 divided by 80. Just to make it easier for me to write, we'll actually do that calculation in the calculator then, because we will need to solve for the interest rate here so that we can then plug it into one of these expressions to solve for X, okay? Now a present value factor to a negative exponent is the same as an accumulation factor. So what we'll actually have here is this. We'll have 1 plus I to the power of 5 is equal to 95 divided by 80. And now we can use our calculator to solve for the interest rate. So let's do that. In this case, we are working with an accumulation factor, so that's going to be a future value scenario. We're saying that if we have $1 and accumulate it for 5 periods, it will become 95 divided by 80. All right, so let's use our TVM buttons. First, you want to clear them out, so hit second future value to clear them out. In this case, the future value is 95 divided by 80, so let's do 95 divided by 80, hit equals. Make that the future value. We have 5 periods we want to work with, so make 5n. And then we're starting with a present value of $1. I'm going to make that negative because when you work with present value and future values, one of them has to be negative if you're going to solve for I or N. All right, so make that the present value, then hit compute interest rate, and there we go. It's about 3.496%. Really, it's about 3.5%. So I'll just write it down like this. We now know that I is equal to about 3.4968%. Okay, it's about 3.5, but I decided to write some more decimals down there. Now what we can do is use that interest rate in one of these two expressions or one of these two calculations to find x. Okay, and these right here are present value equations, so we can just use our calculator again. Be sure to save that interest rate. I'm going to store it in the 1 button. And then let's clear out our time value money. So I'll hit second future value. And now let's just use this one where x is equal to 8,000 times v to the power of 7. If we plug I in for that present value factor, here's what that will look like. X is going to be our present value, and 8,000 will be the future value that we are bringing into the past 7 periods or 7 years. So let's make the interest rate that's currently on our calculator screen here. Let's make that the interest rate. Then we have a future value of 8,000. So let's put in 8,000. I'm going to make it negative. That way the present value comes out as positive. And then we have 7 periods or 7 years. So we're good to go. We put all that information in, hit compute, present value, and there it is. We have now found that x is equal to $6,289 and about 30 cents. And comparing that to our answer choices here, it looks like we can round up to the nearest tens place. So that would be answer choice D, 6,290. Okay, so this was our actual answer right here, but rounding up to the nearest tens place gives us answer choice D. So that would be the right answer for this problem. Next up, we have problem 13. An N-year continuous annuity with $100 payments uses a force of interest delta t, which is equal to 1 divided by t plus 1. Which of the following is a correct expression for the present value of this annuity? And we have 5 different options of what that expression might be. We have 100 times e to the power of n plus 1, 100 times the natural log of n plus 1, 100 times n plus 1 to the power of negative 1, 50 times n squared plus 100 times n, and negative 50 n squared minus 100 times n. Okay, so what I recommend that we do here is sort of ignore these answer choices for now. Let's just try to actually come up with the present value expression ourselves. That's the way that I like to go about these types of problems, where there's not really a numerical answer that you're trying to solve for, but rather an expression. I try to see how close I can get to one of these expressions on my own, and not really analyze these too much. Okay, so let's take a look at our annuity here. We do have a continuous annuity with a force of interest that is dependent on time, right? This force of interest, delta t, is defined in terms of t. We have 1 divided by t plus 1, so the value of the force of interest is dependent on the value of time. So what that means is we are going to be using integration, right? To calculate the present value of this continuous annuity, we will need to use an integral, specifically 2 of them because of the way the formula is structured. Okay, so remember, in general, the present value of a continuous annuity is equal to the amount of the payments, which I'll leave out for now, multiplied by the integral from 0 to n of e to the power of the negative integral from 0 to t of delta t dt, and then you have dt for the outer integral, okay? Or at least this is the way I write out the formula. You may use different variables for your integrals, whatever. This is the integral that you need to use, okay? Now let's actually set it up for our specific scenario here. We do have payments of 100, so I'm going to be multiplying that in here. We'll have that this is equal to 100 times the integral from 0 to n, the number of periods for this annuity, which is just n. We don't know the number of years for the annuity. We just know that it's an n-year continuous annuity. So we're integrating from 0 to n. And then inside the integral, we have e to the power of the negative integral from 0 to t. That doesn't change. That's always the same for present value. But then we're integrating the force of interest with respect to t, which is 1 divided by t plus 1. So we have 1 divided by t plus 1, and then we're multiplying by dt, and then dt again. Okay, so we have 2 integrals that we need to take care of here. We are going to need to integrate this in order to get to one of these answer choices. And let's start with the integral that is in the power of e. We're going to go on a little side mission here, as I like to call it. We're going to work on this integral on its own. We have the negative integral from 0 to t of 1 divided by t plus 1 dt. So how can we integrate this expression? Well, this is sort of your classic example of where you would use the log rule of integration. Remember that the integral of 1 divided by u du is equal to the natural log of the absolute value of u. And then if you had an indefinite integral, you would want to add the constant of integration, but we don't need to worry about that here in this course. In this case, notice that we have 1 divided by t plus 1. That would be our u. We will need to use u substitution here, which is fine. As long as whatever you set equal to u, you can find its derivative within the integral. And in this case, the derivative of t plus 1 is just a constant. It's going to be 1, so that's fine. We don't need to worry about that. U substitution is going to work just fine. In fact, we can almost skip it entirely since the derivative of what we're going to set equal to u is 1. All right, but here's how things are going to go down. We're going to let u equal t plus 1, which means that du dt, the derivative of u with respect to t, is 1, the derivative of t is 1, and the derivative of 1 is 0. So du dt is 1, which would mean that du is equal to dt. So really, we don't need to use u substitution here. We can sort of skip that work. Since we're supposed to be calculus veterans in this course, we're supposed to know our integration rules. Whether or not they're fresh in your head is another story, but we're supposed to know what they are so we can kind of take these little shortcuts if we like. This is not a calculus course. Okay, so what we're going to get here is that this is equal to the natural log of the absolute value of t plus 1, and then we're evaluating that from 0 to t. Okay, so I just took a shortcut there. You technically are still using u substitution, but you're just treating t plus 1 as u. The integral of 1 divided by u is the natural log of u, so we put t plus 1 in those absolute value bars. If the derivative of what you're setting equal to u was not 1, if it was something else, then you would want to proceed with u substitution to make sure you don't make any mistakes with the constants that you'll need to multiply by and whatever else you need to do to make the correct adjustments. So just keep that in mind. But since the derivative was 1, we're good to go here. All right, and another thing to be aware of here is that time is only going to be positive. We're never going to have negative time values. So t plus 1 will always be positive, so we really don't need these absolute value bars. But let's evaluate this at t and subtract the evaluation at 0. It would be equal to the natural log of t plus 1 minus the natural log of 0 plus 1. Right, so we plug t in for t right here, and we're subtracting, plugging 0 in for t. The natural log of 0 plus 1 will be the natural log of 1, and the natural log of 1 is 0. So that's kind of nice. This just becomes 0, and the result of that integral is the natural log of t plus 1. Okay, now I did forget the negative sign. I just realized that. Let's go back here and fix that. We should have a negative in front of each of those parts. All right, so don't forget that, because that's actually going to be pretty important here. If we were to put this answer back in for the exponent of e, we would want to be able to cancel out e with the natural log, but before we could do that, we need to move that negative to be the power of what is inside the logarithm, right? I think we used this property in an earlier problem in this video. When you have a natural log function, you can take a constant multiple from outside of it and make it the power of what is inside the natural log function. So this would be equal to the natural log of t plus 1 to the power of negative 1. All right, so now let's put that back in for the power of e. This will be equal to 100 times the integral from 0 to n of e to the power of the natural log of t plus 1 to the power of negative 1. All right, and then we still have dt for the outer integral. Now, e and the natural log will cancel each other out. They are inverse functions. So we will have 100 times the integral from 0 to n of t plus 1 to the power of negative 1 times dt. But now, t plus 1 to the power of negative 1, if we move that quantity to the denominator to have a positive exponent, you're just going to have this 1 divided by t plus 1, right? That would be 1 divided by t plus 1 to the power of 1. And we already did this integral, right? We already integrated 1 divided by t plus 1, so we can just do it again. I'll do it over here. We know that that would be equal to 100 times the natural log of t plus 1, the absolute value of it, but really you don't need those absolute value bars as we discussed earlier, and that would be evaluated from 0 to n. If you plug in 0, you're going to have 0 plus 1, and so the natural log of 1 is 0, so that term just becomes 0. So really, to evaluate this, you just have to plug n in for t, and you'll find that this is equal to 100 times the natural log of n plus 1. And that right there is an expression that would represent the present value of this continuous annuity. And if you look at our answer choices, it matches up with answer choice B. That right there is the correct expression for calculating the present value of this continuous annuity. If you knew what the value of n was, you could plug it in here and calculate that present value. All right, so that's it for this problem. Hopefully this is a good reminder that you do need to know calculus for some problems in financial mathematics, specifically problems relating to the force of interest and continuous annuities. So make sure that you are sharp on your integration and derivative skills. But with that, let's move on to the next problem. For problem 14, we have yield rates to maturity for zero coupon bonds are currently quoted at 9.5% for 1-year maturity, 10.5% for 2-year maturity, and 11.5% for 3-year maturity. Calculate the 1-year forward rate for year 2 implied by current yields of these bonds. Okay, so hopefully with that last sentence in this problem, you can clearly see that we are working with spot rates and forward rates. We are asked to specifically calculate the 1-year forward rate for year 2. Okay, but before we can do that, we need to know what our different spot rates are. And we were given what they are at the beginning of this problem. That's what these other percentages are. 9.5% for a 1-year maturity or a 1-year term, 10.5% for 2-year maturity or a 2-year term, and 11.5% for 3-year maturity or a 3-year term. So what that tells us is that S1, or the spot rate for a 1-year term, is 0.095 or 9.5%. S sub 2, or a spot rate for a 2-year term, is 0.105 or 10.5%. And S3, or a spot rate for a 3-year term, is equal to 0.115 or 115 for 11.5%. Now, if we draw a timeline here to sort of visualize where these spot rates are and then what forward rate we want to find, if this is time equals 0 and this is time equals 3, then this will be time 1 and time 2. S sub 1 will generate interest for a 1-year term like this. S sub 2 will generate interest for a 2-year term like this, and S sub 3 will generate interest for a 3-year term like that, okay? Those are the yield rates or the spot rates for the different zero coupon bonds that we've been given, all right? That's kind of a common thing that you will see in exam level questions. You'll be given a chart or a list of different yield rates for different zero coupon bonds based on their years to maturity. And usually what's going on there is they're giving you the different spot rates. Or sometimes they'll actually just give you the prices of the zero coupon bonds, and from those prices you could find the yield rates or the respective spot rates. Okay, so just something to keep in mind. That is a pretty common trend in spot rate and forward rate problems. But now what we want to find in this specific problem is a 1-year forward rate for year 2. So year 2 would be taking place between time 1 and time 2, right? This is the first year, this is the second year, so a 1-year forward rate would take us from time 1 to time 2, which makes sense. Spot rates all start at time 0, and forward rates kind of fill in the gaps. So the rate that we want to find generates interest between time 1 and time 2, and that would be the forward rate 1, 2, all right, F sub 1, 2. And the way we calculate that is by using the spot rates for a 1-year term and a 2-year term. Okay, specifically the formula looks like this. F sub 1, 2 will be equal to 1 plus S sub 2 squared divided by 1 plus S sub 1, right? When you're working with a forward rate for a 1-year period, the formula is to take the spot rate for the longer term, which in this case is 2, and use it as an accumulation factor to the power of its term length, and then divide it by an accumulation factor for the spot rate that corresponds to the smaller term, in this case 1, and take that to the power of that term, which in this case is just 1. All right, and then don't forget, I almost forgot, to subtract 1. That's also pretty important. All right, so in this case, here's what we'll have. We'll have 1.105 squared divided by 1.095, and we're subtracting 1, and that will give us our forward rate. So let's pull out our calculator to complete this calculation. We want to take 1.105 and square it, so press the squared button, divide it by 1.095, so 1.095, hit equals, and then subtract 1, and there's our forward rate, specifically a 1-year forward rate for year 2. It is 0.11509 and some more decimals, which turns out to be 11.509%. And that matches up exactly with answer choice B. So that would be the correct answer to this problem. All right, so answer choice B is the right answer. That is it for this problem. Okay, let's take a look at the last review problem for this video. All right, so this is the last review problem for this video here on YouTube. I do have more, but I'll talk about that after we finish this example, so stay tuned if you want to know how to get all of the other review problems. But let's work through this problem first. For problem 15, we have over the next 13 months, Deanna needs to make monthly payments to her friend to pay off a debt she owes. She starts with a payment of $200 1 month from today, and then increases each subsequent payment by $100 until she makes a payment of $1,000. After that payment, she decreases each subsequent payment by $200 until she makes a payment of $200, after which the debt is paid off. For an annual effective interest rate of 4%, what was the original amount of Deanna's debt? Okay, so there's a lot going on in this problem in terms of the payment structure. We know that we're working with some kind of an annuity here. Deanna is making several monthly payments to pay off a debt she owes. We want to find the original amount of that debt, which would be a present value. Okay, so we're taking the present value of some kind of annuity. Specifically, it looks like we're going to have an arithmetic annuity. However, the pattern does not stay the same throughout the entire 13 months that these payments are being made. So let's map it out on a timeline. Let's take a look at what we're working with here. There are 13 periods to take into account. So this will be time equals 0, and then we'll have time equals 13, and then I'll fill in all the dates in between them. And if we look at the payment structure here, it says Deanna starts with a payment of $200 1 month from today. So today would be time 0, which means we start with $200 at time 1. I'll write that in here. We have $200 at time 1. But then she increases each subsequent payment by $100 until she makes a payment of $1,000. So let's write out those payments. We'll have $300 at time 2, $400 at time 3, $500 at time 4, $600 at time 5, $700 at time 6, $800 at time 7, $900 at time 8, and $1,000 at time 9. So now let's see what happens next. After that payment, she decreases each subsequent payment by $200 until she makes a payment of $200, after which the debt is paid off. So at time 10, we'll subtract $200 to get an $800 payment. Then at time 11, we'll have a $600 payment. And then at time 12, we'll have a $400 payment. And at time 13, we have a $200 payment. And that's it. That takes care of all 13 payments for all 13 months. Okay, so that's good. We now know what the payment stream is. Now the question is, how do we calculate the present value of all of these payments? And really, you have a couple different options. In this case, since there's only 13 payments, you could opt to use the cash flow feature of your financial calculator. It might take a little bit of time to put in all of these payments, but really, I don't think it would be too bad, especially considering that the alternative would be to use some arithmetic annuity formulas. Now, this is a review video, so I do want to show you how you would calculate the present value with those formulas. But personally, if I was doing this on an exam, I would probably just use the cash flow feature in the financial calculator, because that would probably be quicker, as you're going to need a couple different annuity formulas to actually value all of these payments. But like I said, this is a review video, so I want to show you how you would do that anyway, because you might encounter some problems in the future where it's not going to make sense to use the financial calculator, because you might be working with more than just 13 payments. You could be working with something like over 100 payments, which then makes doing it in the calculator unreasonable. Okay, so how do we go about valuing all these payments at time 0 using annuity notation? Well, the first thing that I want to point out here is that we have two different types of annuities in the same stream of payments. We have an arithmetic increasing annuity and an arithmetic decreasing annuity, right? We're increasing by $100 every period until time 9, and then we're decreasing by $200 until time 13. So these are arithmetic progressions. They're not geometric progressions because we're increasing and decreasing by set amounts, not percentages. And so what I recommend that we do here is actually split up these payments into those two streams of increasing and decreasing arithmetic annuities. The first one will be from time 1 to time 9, and the second one will be from time 10 to time 13. Okay, so from time 1 to time 9, we're increasing, and from time 10 to time 13, we're decreasing. And so if we start by trying to value these payments at time 0, there are 9 of them. You might be tempted to set it up like this. You might say that the present value is equal to 200 times I, A, 9 bracket the interest rate, which, by the way, what is that? It is an annual effective interest rate of 4%. We will actually have to convert that to a monthly rate. We'll do that in just a second. But for right now, let's just say we have the monthly rate J sub 12. Would this be the right way to calculate the present value of these payments? Well, no, because when you use this notation, the number you multiply by it needs to be the amount of the initial payment and the amount by which every payment increases by. In this case, that's not true. We have an initial payment of $200, but every payment is not increasing by $200. They're increasing by $100. So we're going to have to split these payments up in order to use this notation. And as a byproduct of that, we will also have to include a regular level annuity immediate present value notation. All right, so let me show you how we would go about that here. The way I recommend that you split up the payments is to make a new stream of payments where the first payment is the amount by which every payment increases. In this case, that would be 100. So we have 100, and then just increase every payment by $100. So you'll have 200, 300, 400, 500, 600, 700, 800, and 900. And then whatever is left over should be a stream of level payments. So 200 minus 100 is 100, and you'll notice that the same thing is going to happen for all of these other payments. What's left over after subtracting this new stream from the old stream will be $100. So we have 100 at each moment in time. Okay, so if we want to calculate the present value of those payments, let's start with the level payments of $100. There's 9 of them, so we'll have 100 times A9 bracket J sub 12, because these are monthly payments. We'll find that interest rate then. For now, let's just call it J sub 12. Then we're going to add that to our arithmetic increasing annuity immediate here, where we have 9 payments, where the first one is 100 and every payment increases by 100. So we have 100 times I, A, 9 bracket J sub 12. All right, and both of those notations value the present value of their streams of payments one period before the first payment because they are annuity immediates, so we're good. Both of their initial payments start at time 1, so they're both going to be valued at time 0. Now we need to account for these last 4 payments where we have a decreasing arithmetic annuity. In this stream of payments, the first payment is $800, and every payment after that decreases by $200. And remember, when you use the notation for an arithmetic decreasing annuity, the amount that you multiply by the notation should be the amount that every payment decreases by and the amount of the final payment, which in this case would be 200. Both things are 200, so we're good to go. Every payment decreases by 200, and we end with a payment of 200. So this is pretty simple. We'll have 200 times DA4, because there's 4 of those payments, bracket the monthly effective interest rate, J sub 12, and then we do need to adjust the present value here because this would calculate the present value of those payments one period before the first one, which would be at time 9. So we need to bring that back an additional 9 periods to be valued at time 0. So we would want to multiply by v to the power of 9, where v is using that interest rate J sub 12. Okay, so this is how you would calculate the present value of all of these payments using annuity notations, specifically a level payment annuity notation and 2 arithmetic annuity notations, one where we're increasing and one where we're decreasing. But these 2 notations you can't calculate directly in the financial calculator. You have to do some extra work to actually calculate these 2 types of notations. You can use their formulas, but they are somewhat complicated. If you want to see what it would look like to write out all of these notations with their formulas, and what you would actually have to put into the calculator. I'll have that up here on the screen for you to look at for a couple seconds. Feel free to pause the video if you want to look at it longer, but that's what it would look like, and that's what you would have to put into your calculator. You could certainly do it. I've shown how to do it in my video on how to use a BA2 Plus calculator. My general advice is just to break up the formulas into different parts. Calculate the annuities, subtract what you have to subtract or add what you have to add, and then divide and multiply where necessary. But admittedly, in this specific problem, that would be pretty time consuming. I wouldn't recommend you do that. If you had a lot more than 13 payments, you would probably want to do that. That would be better than what I'm about to do to actually solve this problem, which is use the cash flow feature. That is good if you have a reasonable amount of payments. We already sort of discussed this at the beginning of this problem, but if you had a lot of payments, then this method of using the annuity notations would be your best bet. But since we only have 13, I'm just going to use the cash flow feature in the calculator. And so let's do that, but before we can do it, we do need to know what our monthly effective interest rate is. So let's find that. We were given an annual effective interest rate of 4%, so we know that I is equal to 0.04. We need to find J sub 12. So to convert that, we'll take the annual effective interest rate, 0.04, and set it equal to 1 plus J sub 12 to the power of the number of times it would be convertible in a year, which is 12, and then you want to subtract 1. Okay, so to solve for J sub 12, you want to add 1 to both sides, so you'll have 1.04, and then you want to take the 12th root of both sides of the equation and subtract 1. All right, so J sub 12 would be equal to 1.04 to the power of 1/12 minus 1. All right, so we'll do that in our calculator as well. So let's pull out the financial calculator and calculate the present value of all of these payments. Again, just to be clear, if I was actually solving this problem on an exam, I would not have bothered to write out these notations. I'm just doing it for the sake of this video to help you review. I would have immediately gone to the cash flow feature since there's only 13 payments. But now, first order of business is to calculate this interest rate. So we need to take 1.04 to the power of 1/12. That's going to be a little bit tricky because it is a fraction. So let's do 1 divided by 12, hit equals. There's 1/12. I'm going to store that in the 1 button. Then we'll take 1.04 to the power of recall 1. Hit equals. There it is, except we need to subtract 1. Now there it is. Then you can multiply by 100 to get the percentage form, and it's 0.327%. Okay, now I'm going to store that in the 2 button. We'll come back to that when we need it to actually calculate the present value. I just want to quick show you another way that you could have converted that interest rate. If you didn't want to do all that extra math I just did, you could go to the interest rate conversion menu. So you'd hit second and then the 2 button. And in here, you would want to go up to effective, put in 4%, because that was what the annual effective interest rate was that we got. Go down to C/Y. That tells you how many times you want your new rate to be compounded per year. So I'll put in 12 for monthly. Then go down and hit compute. Now that gives you the nominal rate. So then if you divide it by 12, there is your effective monthly interest rate. You got the same thing, 3.27%. Okay, so that's another way that you could have gotten that same rate. Now, let's actually calculate the present value of our cash flows here. Go to the cash flow menu, clear it out. So hit second, clear work. And at time 0, we have nothing. So just move on to C01, where we have a payment of $200, and then we'll do 300, 400, 500, 600, 700, 800, 900, and 1,000, and then we'll decrease by 200 till we get to 200. Okay, so I'm going to go through this pretty quick to kind of show you how fast this can be. So C01 is 200, hit enter, go down, leave all of the frequencies at 1. None of them are happening more than once. All of our cash flows are happening one time, so leave the frequency alone. But then go down to C02, where we'll have 300, enter. C03 is 400, enter. C04 is 500, hit enter. C05 is 600, enter. C06 is 700, enter. C07 is 800, enter. C08 is 900, enter. And then C09 is 1,000. All right, so now those are all the increasing payments. Now we need to decrease by 200. So C10 will be 800, enter. C11 is 600, enter. C12 is 400, enter. And C13 is 200, enter. Okay, now what you want to do is hit NPV. and put in the interest rate from earlier. So hit recall 1, I believe is where I stored it. Oh no, that's 1/12. So hit recall 2. There it is. That's the interest rate that we calculated. Hit enter and then go down to NPV, hit compute, and there is the present value. That's a whole lot easier than if you were going to try to plug in all of the other information from the annuity notations. Trust me, that was quicker, even though it seemed like it maybe took a little bit long. That's going to save you a lot of time on an exam if you do it this way. Okay, but regardless, we found that the present value was equal to $7,222. And I guess there's about 75 cents there. So that would round up to $7,223, which takes us to answer choice C. Okay, so that was the final answer to this problem. That's the present value of this stream of payments for 13 months. The debt that Deanna owed to her friend was of that amount, $7,223. Okay, so with that, this was the last review problem for this video here on YouTube. However, I do have 15 more review problems just like these, but obviously different problems that will test your knowledge of financial mathematics. I have those available exclusively on my membership site, JK Math Plus. So if you want to get some more practice and do some more review problems, feel free to look into becoming a member. You can find all the details on the membership site and how to join at jkmathematics.com/plus. There's a whole lot more on there than just 15 more review problems for this final exam review. There's also extra review problems for my unit review videos, as well as some other bonus videos related to financial mathematics. And there's dark mode versions of all of my videos. If you're somebody that likes black backgrounds and white writing, I have all of my videos inverted that you can watch on the membership site. Okay, and there's a lot of other content for the other courses that I cover on my channel, including Calculus 1, 2, 3, and any other courses I cover in the future. And I plan on adding a lot of other features to the membership site in the future. So it's definitely something that I think will provide you with a lot of value. Not to mention that any comments you leave on those videos are guaranteed to get a response from me. All right, but with that, that is it for this video. If you had any questions about the problems in this video, please feel free to leave those in the comments. But if you don't have any questions, then that is it for now. So I will see you next time.